everyone. Hello. Hello. Otherwise, I can hold in my hand. It's fine. It's fine. I can do that. Hello. Yeah. Good morning, everyone. Uh, Thank you, ma'am, for that very generous introduction. Thank you very much. And before I begin, thanks to the Department of Chemistry for this kind invitation and also to the very warm hospitality. Thank you very much. So, as ma'am told, I'll be talking about electrospun membranes. So electrospin is actually a past participle of this verb electrospinning. So something which is made out of electrospinning can be called as electrospun. That's why we use the word electrospun. So electrospinning is a very versatile technique for the preparation of nanofibers from polymer solutions. So basically you start with a polymer solution which actually is pushed through a syringe, and then very high voltage is applied, and then this polymer solution is getting converted into a film of controlled porosity and controlled functionality. So that's what I will be discussing about. So before I begin, how can I get it like full screen? Display settings isn't working now. Or is it like this? I am duplicate. Then PC only. Then PC only means this only it will show, no? Just a second. I will escape from here. Oops. Okay, let me try from here now. Okay, sorry for that technical glitch. So before I begin, I would like to just briefly introduce the place where I am coming from. Christ University is a university, it's a private university in Bangalore. We were established as a college in 1969. And then in 2008, we are converted into a deemed to be university. And then we have 6 campuses, 4 within Bangalore, and then one in Pune and one in Delhi, NCR. So, like in terms of number of students, we are a kind of big campus, like 20,000, around 20,000 students are studying in the campus. So this is where I come from, and then we have like very active science departments like chemistry, physics, life science, and we were well known for teaching before we converted into university, and the research is actually building up now. People of research background are joining as faculty, and then very active research is happening. So this is where I come from. Then about the content of the presentation, I will just try to share with you. I'm not an expert in electrospinning because the electrospinning process is actually more physics than chemistry. So I don't know much about the fundamental or theoretical aspects of it, but the practical aspect of it, as a chemist, as a material chemist, how we can use electrospinning to get functional nanofibers which can be tailored for applications like sensing, separation, etc. This is what I will try to explain. So fundamentals of electrospinning. Electrospun fibers for sensing applications, sensing of pollutants, sensing of food damage, sensing of gases, etc. And then electrospin fibers for separation applications also, for the environmental remedial application. So, and then if time permits, I will share some other works which is not directly related to electrospinning but is related to fibrous membranes. Okay, so this is the plan. Let's see how it goes. Now, to begin with, I would like to start with a historical perspective. So, I think you are familiar with this idea or notion in history, where various ages of our civilization, ages of the progress of mankind, is related to different type of materials, right? So, we talk about Stone Age, where we were able to, handle stones only. Stones were our, materials of use, materials of functionality or utility. Then Bronze Age, Iron Age, Middle Age, Industrial Era, and then now we talk about Info Age also, right? So Silicon. So within Info also there are like sub varieties like Facebook generation and Instagram generation, right? Two different generations. So within that also you have these variations. So what message it tells us? The thing is like our ability to process different type of materials, our ability to design different materials, and our ability to tap the functionality of these materials actually is directly correlated to our technical capabilities or scientific capabilities, right? So if stone is the only thing you can manipulate, stone is the only thing you can design and construct, your ability or your technological advancement is limited to that. The more number of materials you have, the more ways in which you can control the property of a material, the more useful it's going to be, and more customizable these things are going to be. And then also it's very much related to the structure property relationship also. The property of the material is dependent on the structure of the material, right? And how it is related is actually the subject matter of chemistry and physics, right? How tiny variations in the atomic structure, molecular structure, or assembled structures can vary the functionality a lot. So how to do this? How to do this in a very controlled and regulated way is the challenge of any material chemist, right? So having said that, the first example of thinking of what could be the structure property relationship, actually very ancient example from philosophy, Western philosophy. Thales, one of the ancient Greek philosophers, he believed that everything in this world is made up of water. And what is the logic? Because when he sees water, water can be present in three different forms. Water can be present in the form of water, liquid, and it can be present in the form of ice, and when you boil it, it's actually converted into gas also. That's the only material he knows like which can exist in all the known three forms of matter. So then he postulated that everything is made up of water, one or other form of water. Only thing is there is a difference in property based on the structure or based on the stage or phase of the material. So this could be the first example of rational thinking about what is the structure property relationship of materials, right? So we came forward a lot, and then like we understood a lot of things about the structure property relationship of materials, how properties of materials are dependent on the structure. Now, for example, very impressive example, if you consider silica, silica in different different dimensions can be utilized for very different applications. For example, the glass we use is silica, right? What is the thickness of glass usually? Usually millimeter, right? And then the silica gel you find in the packages where it's used for the absorption of moisture. There also you have some millimeter size particles, right? And then when it comes to micrometer, you have these semiconductor chips and piezoelectric material. Again, it's the same material, silica, SiO2. Chemically, it's same, but very different application, very different functionality also. Then silica nanoparticle, if you take silica nanoparticle can be used for UV blocking applications, for painting applications, etc. Same material, but a different dimension and a different application. Then you have molecular sieves based on silica, the cage structure. Yesterday sir was talking about the cage structures, right? So with silica you can do that. So see, like the same chemical material made in different morphologies, different size, dimension, actually provides very different functionalities and very different applications. So this tells that if you have a strategy through which you can control the size of the material and shape of the material and assembly of the material in a very intricate and predictable way, you can actually decide or design the property of the material. So this is the scope of a chemist or a material scientist in the application related to materials. You control the size, you predict the performance, and use it for the practical applications. Okay, so that predictability or the determinism in that is very important. Now, when it comes to nanomaterial, so how nanomaterials are different from other class of materials, as you know, size-wise, it comes between the bulk state material and the molecular material. So the size is between, molecular materials are having angstrom level size, while the bulk state material are having micrometer or even millimeter size. So if the size is in between these two, between the angstrom and micrometer, the materials start showing very different properties which are very dramatically or drastically different from the properties of either molecular material or bulk state material. And not only that, for example, gold, as you know, is a very shiny yellowish type of metal in the bulk form, right? But when you make gold in the nanometer dimension, what is the color of gold nanoparticle solution? Anyone knows? Could it be yellow? No, not yellow. If that's the case, I won't ask this question, right? Yeah. So then, what could be the color of gold nanoparticle solution? Red. Yeah, somewhat similar to red. Yeah, usually pink to red you can change. Yeah, usually it is purple, some variety of purple, right? So again, since you told pink to red, right? What does it mean? So if you ask the color of bulk gold, it cannot be pink, red to yellow. It's always yellow. But gold nanoparticle can have this, variety of sizes. So variety of colors. Actually, this color can be controlled if you can do synthesis of gold nanoparticle in a very precise way. So if you can control the diameter of the gold nanoparticle, the surface plasmon absorbance changes, and then once the absorbance is changing, the color also is changing. So the nanoparticles usually have size-dependent properties. That's why people are interested. You can actually make them in a particular way. Whatever property, whatever photophysical property you want, you can actually control it by controlling the size of it. Another one, it actually has shape-dependent property also. So size is not the only thing. If you can control the shape of it, for example, gold nanoparticle and gold nanorod, they are having very different properties. Gold nanorod is actually having two absorption peaks, while gold nanoparticle will have only one absorption peak. So the same material made in a different shape will have a different property. And then self-assembly. So if you talk about nanomaterial, so if individual nanoparticles are having one particular application, we can never use a single nanoparticle for a practical application, right? We are not, walking around with a nanoparticle to apply somewhere. We cannot handle it actually. So we can handle only assemblages of these nanomaterials. You need to have a bulk state assembly of this nanomaterial, and then the property of the assemblage can be different from the property of individual materials. The way in which you arrange it, just like people, right? When you're sitting here, your property is different. But when you're sitting in a party of your colleagues, your property is different, right? Just like that, the assembly of nanomaterial, the total group collective property is very different, and then that can be controlled in the way in which the assembly is done. Okay, so they have self-assembly related property as well, and also they have very different bio-nano interface. How this nanomaterial interact with biological system is very different from how the bulk state material are interacting with. For example, silver nanoparticle is known to have very good antimicrobial activity, antibacterial activity, which is not present in bulk state silver. And then you can actually control that activity also by controlling the size and surface functionality, etc. So yeah, actually I should have started with surface. The most important property of nanomaterial is actually the surface property of nanomaterial. Why? Because once you make material in the nanoscale dimension, most of the atoms are surface atoms in those systems. This you already know, right? You might be studying in your syllabus. So in bulk state material, if you take the percentage of atoms on the surface, it's very minimal. and it's not having significant contribution to the overall property of the material. But in case of nanomaterial, the overall property is decided by the surface atoms only. So the properties of nanomaterials are actually very much dependent on surface, and even very small changes on the surface actually can change a lot of properties of the nanomaterial. So surface of nanomaterial also is very important. So basically scientists, technologists, and people who are doing research in nanomaterials are very much interested in them due to these surface property, size dependent property, shape dependent property, and self-assembly related property, and bio-nano property. This is very much different from what bulk state materials are having. Now coming to nanofibers. So what are nanofibers? Nanofibers by definition like fibers which are having diameter within the nanoscale dimension, diameter within 1 nanometer to 100 nanometer. That is a loose definition of that. Okay. So what's the difference between normal fiber and nanofiber? Size is there, but usually just like how you have size dependent or shape dependent property of metal nanoparticles, you don't have that type of a property for the size dependent property for the nanofibers. But what's special here is like when you have this assembly of these nanofibers in the form of a membrane, the porosity usually comes within the nanoscale dimension. So the porosity in nanoscale dimension actually is a nanoscale vacancies, right? Nanoscale absences. And if you can control this porosity, so like the presence of certain things are absence of certain things are very much important, like the presence of certain things. So you have nanoscale, like people also, right? Absence of some people makes us happy, and vice versa also. Okay, so nanoscale nanofibers, when you assemble, you can have nanoporosity. This nanoporosity can be controlled, and then this porosity behaves in a very different way than the normal microporous membranes. So that's why they can be used for many different applications. In context of electrospun nanofibers also, this is actually what makes that system very important, because when you do the electrospinning, you have this membrane, and it's made up of nano materials, and then the porosity, the gap between the fibers, can be controlled by adjusting certain parameters of this fabrication process. I will come to that. You will understand it more then. Okay. Now coming to fibers, fibers. We have a very long history of using fibers, like centuries of history we have about using the cotton fiber, silk fiber, many natural fibers for practical applications, right? So the central or core property of the fiber is like they have high length to thickness ratio or aspect ratio, more length than the width. This is the idea. And then they have flexibility. They are, if you go for natural fibers, they are economical, and they have sufficient strength and length. They have tenacity. That means the resistance to mechanical force. And then most importantly, you have the dyeability also. Dyeability means you can actually incorporate chemical compounds into this, thereby making color to that, and also other functionality to these fibers. So that's what makes fibers very interesting class of material. And then, yeah. Okay, so there are natural fibers and synthetic fibers. They can be classified according to the chemical composition, according to the strength of it, according to how flexible it is, how stretchable it is, etc. And also another way of controlling the property of fiber is you can actually start with a normal fiber. You can coil it. The strength of it increases, right? With that coil, you can actually make if you have two coils together, coiled together, you have a yarn. And with the yarn, if you are actually doing the fabrication of cloth type of structure, you have fibrous substrate, right? So it can be like very, very strong, because it can withstand a lot of weight if you carefully design the structure of it. So this is why people are interested in investing on fibers. Okay, now about the modifications. As material chemist and material physicist, we are more interested in how to control the properties of fibers. So two type of modifications you do. You can do physical modifications and you can do chemical modification also. So the physical modification is actually heating, ultrasound treatment, leaching, surface adsorption, heating plus stretching, and also in chemical treatment you have carbonization, sintering, plasma treatment, chemical cross-linking, mineral deposition, etc. So chemically or physically you can change the property of the fiber by appropriate treatments. Then I think I will directly go to our topic without wasting much of our time. So, sorry, I'm not very practiced with this thing. So I just remember something which I read, not related to chemistry. Kathak, right? Kathak is traditional dance form from Orissa, right? Odisha. So most of the postures in Kathak is a two-dimensional posture. They don't do this more often. They do mostly like this. It's because most of the postures are taken from these sculptures in this Konark temple. And it's very difficult to make, a sculpture which is actually pointing the hand forward. I don't know if it is true or not, but I read it somewhere. So just like that, my gestures are kind of I can't do this. My gestures are fixed here. So yeah. So that means like if my talk is boring, no, I think like the voice is not reaching. No, it's okay. I just I wanted to share something which crossed my mind. I'm okay with it. No issues. I'm not going to do a dance. Yeah, but you can. I mean, if you feel very excited about the topic, you can dance about it also. But don't run out. You can run out also. That's another physical activity. Listening to this. Okay, fine. Okay, electrospinning is a process or a fabrication technique which is used to make nanofibers. How you do it is very simple. Conceptually or procedurally, it's very simple process. But my students will not agree because they are the one who are doing in the lab, and then I am the one who is pushing them. It's not easy to standardize the parameters for this, but conceptually it's very simple. Electrospinning, what you do is you have a polymer solution. Okay, so this polymer solution is filled into a syringe. Okay, and then the syringe is connected to a very small syringe tip, which is called spinneret in the technology, in the terminology of electrospinning. And then this spinneret is connected to a very high DC voltage. And then this polymer solution is mechanically pushed down with a controlled force. Usually you use a syringe pump. Syringe pump actually can exert a controlled amount of force at a given time. So usually it's given by like this much milliliter per minute. That's a unit of this, flowing of this polymer. So the polymer is flowing like this, and the voltage is applied, and then you get the deposition of nanofibers. You won't see nanofibers. You will see a film. You will see a membrane, which when you take to the SCM or SCM is usually required, you will see structures like this. So what's happening when the polymer solution is pushed down and electric voltage is applied, that's a DC voltage. Two opposing forces are there. One is capillary force. Capillary force want to retain this droplet in the spherical form in order to have minimum energy, right? So in order to minimize the surface area, in order to minimize the surface energy, it actually want to remain as a droplet. But when you apply this voltage, DC voltage, static electricity is built upon. So like, static electricity is increasing. So they are like opposing forces, capillary forces acting in this way, and the electrostatic forces acting in this way. But you keep on increasing the voltage. At some point, this will dominate. Then what will happen? The charge need to discharge. It need to dissipate. So how it can be done? The droplet will come out in the form of a small jet. And that jet is actually called a Taylor cone. From the Taylor cone, the jet is coming out. When the jet is coming out, the solvent in which the polymer is dissolved is getting evaporated. Then what's remaining? Solid polymer. In what form? Very thin, thread-like form. And that thread-like form is getting collected to the collector. Why? Because the collector is connected to earth. you have high charge and then it want to neutralize. That's why it will get deposited on the collector. Okay, so this you can do in two different ways. One is the vertical format, other horizontal format also. So based on like what type of film you want, this is what you do. Very simple process. You can see this is the horizontal configuration. You can see the spinning tip. This is the Taylor cone from which the fibers are emerging, and then there is this flow towards this oppositely charged electrode, and then the fibers are formed through the evaporation of the solvent. Okay. Now I think a video is there which will explain these things in a more clearer way. You can see the production. And this is a rotating collector. Why we need a rotating collector? Can you use your logic and tell me? Yeah, what is the advantage of using it? Why can't you have a stationary collector? Yeah, so because like if you have a stationary collector like this, the deposition is not happening uniformly everywhere. So you want like very uniform coating and then like a continuous film. So for practical application, it's always better to have a film of uniform thickness. So that's why you keep on rotating it. And then that rotation speed also actually decides the quality of your film. That's another parameter we need to customize. We need to optimize. Okay. So yeah, I was distracting you from the video. So finally, how you get it is like this. One more time, I will play it. Okay, so now it went to a real video. So it's usually on an aluminum foil, and this is actually a very thin film. Usually it's very easily detachable if it is a thick film. And then you can cut in appropriate size, and then that comes as a freestanding film. The thickness of it actually depends on the deposition time. The more you deposit, more thicker your film will be. Yeah, it's very different. Spin coating, you are just rotating it, and due to the centrifugal force, you have this uniform deposition. Here, due to the application of, and also here the internal structure of that is very different. You have nanofibers. In spin coating, it's just a uniform film without any pores. Yeah. And then like getting the polymer solution to spin as fiber is a very challenging task. Not every polymer will spin. You need to have the right combination of polymer and solvent. You need to have the right voltage. You need to have the right distance between the tip and the collector. Many things you need to customize. Even then, some polymers are not spinnable. In that case, they will be undergoing something called electrospraying. Electrospray means it gets sprayed and then you get deposition of nanoparticles. That also is useful for certain other applications, but electrospinning and spraying are slightly different. They are differing in the end product. Here you have a continuous film which is made up of the nanofibers. Okay, so this is how the electrospun membranes will be collected, and then what's happening in a chemical level. So initially this polymer, when you are dissolving it in a solvent, it's actually having very random organization. So the polymer strands are jumbled, not organized. But once you apply this voltage, and then due to the formation of this Taylor cone and this ejection from the tip, you have very good orientation of the, you are achieving orientation of the polymer film. So this is a much organized structure than the normal one. So yeah, this is something which happens. This I already told. Like you have a droplet initially in the spherical format, the spherical shape, which get converted into conical, and then finally into a nanofiber. Okay. Yeah. So why electrospinning is considered or envisaged to be a good technique? When you compare other methods which are available for the formation of nanofibers, drawing is one method. Like suppose you want to make ultra long polymer fiber. So what you do is you start with a polymer solution, come up with a needle, touch it there, and then pull it as long as you can. So what will happen? It will elongate in the form of a nanofiber. Like if you elongate enough, you get diameter in the nanoscale dimension. Advantage is you can have actually very, very long fiber. Disadvantage is it's very difficult to scale up, right? If you want to make such a, a cloth out of such fibers, you will use your entire lifetime to make it, right? So because one fiber at a time only you can prepare, right? It's very slow process. Then you have template synthesis also, like you have patterned openings through which the solution is pulled down, and then the fiber, it's coming in the form of fiber, nanofiber, if the pores are nanoporous. So if these are nanoporous filters through which you can push down, just like there are certain snacks we make like that, right? You have some maida, atta or rice, and then you push it through something and it comes out in the form of different shapes, right? So yeah, similar to that, but doing it in the nanoscale dimension. Then another way of doing it is phase separation. You have a polymer which is dissolved in a solvent, and the solvent is not a very good solvent. And you add another solvent onto that, and these two solvents are not miscible with each other. Then you have an interface. And this polymer is actually having some affinity to the solvent which is on the top. So what will happen? This from the solution, it will move up to the interface, and the interface you get a film, and that film can be in the form of nanofibers if you add certain surfactant, and also some soft templates which actually controls the morphology of the interface. That's one way. And another thing, self-assembly. You start with molecular precursors which assemble in a particular way, and the assembly is formed in the form of a nanofiber. But there actually you have more molecular level control or precision over the structure of it. But again, it's not possible to make such a fiber out of all molecules. So because like the self-assembly, yesterday sir was mentioning about how difficult it is to control the assembly of molecules. But if you have control, that control is a very precise control. That is the advantage. And then compared to electrospinning, whatever disadvantage you have for all these are addressed, and then electrospinning is superior in that. You can actually scale it up, you can actually mix the polymer together, and you have a composite fiber. You can add some nanoparticles into this, so that this property of the nanoparticle also is incorporated into the fiber. So all these advantages we have when you use electrospinning. Okay, so yeah, this is a comparison between different methods for the preparation of nanofiber membranes. Drawing, template synthesis, phase separation, self-assembly, and electrospinning. And can this process be scaled? Among these, only electrospinning can be scaled up. You can do it in an industrial scale also. You can actually have a machine where you have multiple syringe, multiple needles, multiple spinnerets working together at the same time. Then you suddenly get large area of the fibers. So it's perfectly scalable. And is it repeatable? Yes, all these are repeatable. Once you customize, once you optimize the condition, you can actually repeat it. And then is it convenient to process? These four are. Phase separation is not. Why? Because you use large amount of solvent. And also if you want, like say 1 meter square of this film, you need to have a beaker of 1 meter square radius, right? You need to have like 2 layers of solvent, large amount of solvent is used. Also, once the film is formed, how to separate it from the interface? It's a challenging task. Then control of the fiber dimensions. You have very good control when you are using the template synthesis. Just like that patterned opening, the diameter of the membrane depends on the opening size. In electrospinning also you have very good control once you optimize the electrospinning conditions. Other places, for example, phase separation, you are not directly controlling the size of the fiber, and self-assembly also, it's a self-regulated process, and we have less control over it. So you can see a tick mark is there for electrospinning in all these categories. Not just because I'm talking about electrospinning. Tomorrow I will go and give some presentation about this. All this tick mark will be moved. It's not like that. You can question me also if you feel like I'm very biased about my own work. Okay. Okay. Then, are we doing good with time? Oh, I think up to 11 o'clock, right? So I will try to finish as soon as possible. So yeah, here when you do this spinning, you can actually use different type of needles. For example, if you have a one needle inside another needle, okay, and then it's connected to the outer area is connected to one syringe, inner area is connected to another syringe. Now when the fiber is formed, you have a core shell structure type of fiber. So you can actually think of all possible designs for the needle. Different type of openings, different type of combinations of needles will give you different morphology. Another one, you can think of needleless electrospinning also. You don't always need a needle. You can actually use, cylinder spinneret. You have a polymer solution. This cylinder is moving like this, and then voltage is applied. So this solution is just converting into a film, and it's actually thrown out like this. So different type of spinnerets you can use. This is called, the other one which I mentioned is like coaxial. This is a biaxial syringe. You can see this solution is passing through this needle, and this is going to be like this. So the core of that will be this solution, and the shell will be this one. And you can actually build it on. I mean, like you can have triaxial also. Different type of combinations you can have. So you have like total control over the composition of the polymer film. That's the message I want to tell. Then what are the things you need to optimize for this? You need to optimize the concentration. So three different parameters. One is solution parameter, other is process parameter, the final one is surrounding parameter, surrounding conditions. So about the solution parameters, you need to control the concentration of it. How much gram per milliliter you are dissolving it in the solvent. And then solvent volatility, how volatile your solvent is. Then dielectric constant of the solvent. Is it polar, non-polar, polymer is polar or non-polar. Normally you cannot use water as a solvent, because water itself is having very high dielectric constant, which actually messes up with the voltage which you are applying through the DC. So it's not a suitable solvent. Also water is evaporating very slowly, so you will not get quick evaporation of it. You may need a heating condition also. So usually non-polar solvents and volatile solvents are giving you good results very easily. But certain polymers are, suppose you want a conductive polymer nanofiber film. It may not be soluble in hexane or toluene like that. You may have to use some polar solvent also. And sometimes you may have to mix the solvent so that you get a appropriate polarity for the process to happen. Okay. Then process parameters, electric field strength, how much voltage is applied, flow rate, with what speed this solution is pushed through the needle, and tip to collector distance, between the tip and collector, how much distance is there, and syringe diameter, how much big is the opening of the syringe, and electrostatic potential. Then these are the most challenging, and these are the things which students don't like at all, because if you do the experiment today, you optimize it for certain condition, the same condition, same parameters you are using tomorrow, you may not get good quality fibers, because the humidity is not in our control, temperature is not in our control, then pressure, atmospheric composition, local atmospheric flow also, like if you have a fan or AC, and then like if your system is an open system which is exposed to the environment, exposed to wind and all, you will not get same results always. So you need to maintain the atmospheric conditions as consistent as possible from experiment to experiment for the consistency of your results. Okay, history of this. Actually, we had a history, very long history of electrospinning. In 18th century, one scientist, Stephen Gray, he was the first one to observe electrohydrodynamic atomization of water droplets. Water droplets is actually evaporating when you apply voltage. And also you can see William Gilbert in 17th century reported the formation of cone-shaped water droplet. Normally water droplet is spherical, right? But when you apply voltage, he observed like some conical shape is produced in the water thing. And then like, people started building on it, and then we are here. And today also we are discussing about it, because still it's very relevant. So, okay, I'll skip these things. And then why these electrospun membranes are considered as important or suitable for the different type of applications. Usually we can classify it into two categories of application. One is sensing application, other is separation application. So why they are considered as suitable? Because they have a highly porous structure, so which makes like very high surface area system, and it's easy for this membrane to be in contact with your analyte in any form, whether it is gaseous form, whether it is liquid form. The porosity gives better area of exposure, which is actually useful for better sensing. And then large surface to volume ratio. Most of the atoms are present on the surface, and then you can always make hybrid compositions. You mix things, whatever you can mix with a polymer solution, and which is not interfering your spinning process, can be used as a additional component or additional material in the nanofiber membrane. So these are the interesting fact. Okay. Then what are the sensing applications? Usually we do gas sensing, heavy metal sensing, and also food quality monitoring. So food quality monitoring is a very emerging field. What you do is, as you saw in that video, finally you get in the form of a cloth. Okay, so this cloth can be used as a packaging material. And in food industry, people are interested in having this, smart food package. Mean a packaging of the food which automatically tells you about the quality of the food inside. So if the food is damaging, the package color also is changing. So this type of things you can very easily make with electrospun membrane. So if I have time, I will show one or two of that which we made in our lab also. Okay, sorry. Then about optical sensing, like you can incorporate materials which are showing emission, and this emission is sensitive to the presence of an analyte. In that case, you can use actually fluorescence quenching or fluorescence enhancement as a detection tool if you can incorporate that material. And it can be scattering based analysis also, like surface enhanced Raman spectroscopy, which actually people claim like they are able to even detect a single molecule using SIRS. How is it possible to detect a single molecule? Are you studying Raman spectroscopy in your syllabus? No, not yet. Okay, maybe in future you will study. So regular Raman spectroscopy, that also is very difficult. It's not easy to get if you don't have a very powerful laser radiation. Right? Raman spectroscopy is based on scattering. Right? When you give radiation to a sample that's getting scattered, the majority of scattering events happens as a elastic scattering, where there is no change in the energy. That is called Rayleigh scattering. And then there is inelastic scattering. Two type of inelastic scattering: Stokes and anti-Stokes. Stokes means the energy of the radiation get decreased after the scattering. Anti-Stokes means energy of the radiation increases. So normally the inelastic scattering is happening less in number. So if you use a normal photon source, you will never be able to detect Raman effect. You need a very powerful laser. Then only you will be able to detect some Stokes and anti-Stokes lines. Okay, that also, regular Raman spectra is limited for a concentration of the analyte in micromolar region. Minimum you can detect is micromolar. But if you have a surface enhanced Raman spectroscopy SIRS platform, where usually you have a nanomaterial or nanostructured surface, where you have something called Raman hotspot. So in this hotspot, what's happening is the electric field of the incoming photon is getting amplified in certain nano cavities. So whatever you give energy is focused into very small cavities, and if you have even if you have very small concentration of the sample there, you get very high energy from it. I mean very high signal from it, very high intensity signal from it. That's called the SIRS. And then SIRS need this surface enhanced Raman spectroscopy need these nano cavities. So if you can incorporate these metal nanoparticles into electrospun membranes, or you make electrospun membranes and coat it with metal, then you have a nanostructured surface which is very much applicable for the SIRS activity. So how do they, I started from this question, like how do they know it's single molecule detection? How do they claim single molecular detection? If you can detect concentration up to 10 to the power minus 23. That is in the Avogadro number region, right? So, and then 1 by 6 into 10 to the power minus 23. What is that actually? That's one molecule. right? 1 mole contains 6 to the power 6 into 10 to the power minus 23, and 1 by 6 into that much molar will represent 1 molecule. So people are claiming we are detecting 1 molecule, but there is like lot of criticism against it, because like when you do this search, it's not like from every point you can detect 1 molecule. This is like a lottery. In a sample, one area you may get it, but definitely you will be able to detect, nanomolar or femtomolar also. It's very easy. Then electrospun, yeah, I kind of deviated a little bit. Electrospun membrane also can be used for the search substrate. How many more minutes I have? I can continue. I can continue up to evening if you. But I have a flight in the evening. That's why. Is it interesting? Do you find it useful? Then I can continue for 10-15 minutes. Is that okay? Yeah. This is what happens. Like if you know fundamentals, and then if the audience is very receptive as you are, not sleeping. I think maybe it's because morning, but anyway. Yeah, I kept on explaining it. Okay, this I will skip and come back to it later. And then the second set of application electrospun membranes can have is for the separation, because you have a membrane of very controlled porosity through which materials can pass, and then which material can pass through it you can decide by controlling the porosity of it. How to control the porosity? You actually change the deposition time. More deposition means more number of fibers per unit area, and the porosity is smaller and smaller. So you have absolute control over what can pass through the filter and what cannot pass through the filter in the size parameter. And also if you can control the surface chemistry of these fibers, you can make hydrophobic or hydrophilic fibers. If it is hydrophobic fiber, what will happen? The hydrophobic thing will be very easily passing through it, because it's actually having affinity for that. And if you are making it hydrophilic, the reverse will happen. So if you have a mixture of oil and water, which is actually a very serious environmental issue, a lot of oil is being spilled into our water bodies, and then how to easily separate it. So if you have a membrane which is custom made like this, and you pour this solution through it, and then after filtration, oil and water is totally filtered. I mean, oil only is passing through it, means oil is separated from water. So for oil water separation is one thing. And another, people are able to control the size of the pores and also the chemistry of the pores. They are using it for desalination application. Desalination means removal of sodium chloride or removal of inorganic salt from the drinking water, right? So this can be used for that also. That's why a lot of people are interested in this. Then oil water separation, wastewater treatment. Lot of inorganic and organic pollutants are there in water, and if you have some specific adsorption of a species to this membrane, you can actually use it for the that application. And then bioseparation, smart food packaging. This I already mentioned before. Now, coming to what we did in our lab, one work which we published last year in Chemical Engineering Journal. So here we wanted to make a membrane which is actually capable of doing oil water separation, dye degradation, and antimicrobial property as well. So these three properties we wanted to incorporate in the single fiber. So intuitively, what could be your plan? The plan is like you mix all these materials which are giving you these properties. So we worked with a polymer mixture which is actually cellulose acetate and polyvinyl pyrrolidone. Into that we incorporated zinc oxide particle and also silver doped zinc oxide particle. Three different systems we studied. The polymer solution is a mixture of either this or this. Okay, Ca means cellulose acetate, PVP means polyvinyl pyrrolidone. So certain polymers, they are not spinnable, but to make them spinnable, you need to add it or mix it with another polymer. So that's why we mix this PVP and cellulose acetate, and these are the optimized conditions. And this is one representative image of the film we are getting, SEM image. And then the instrument we used is this one. This is a custom made machine which we purchased from some company in Chennai. So this cellulose acetate PVP membrane, that's not physically very strong. To make it more strong, you can do some process which is called deacetylation. Deacetylation is this process. It's actually basically a base treatment in ethanol. So deacetylation is happening. You can see the color is changing, but the physical strength is increasing. Also, the hydrophobicity is increasing due to that treatment because acetyl group is removed. Then, okay, so these are the physical characterization, how long they are, how wide they are, etc. We studied. It's actually confirmed using EDX also. Then, yeah, these are just structural characterization. I'm skipping. I'm just going to the application part. So, for the oil-water separation, this membrane need to have a property which is called underwater super oleophobicity. You know what is hydrophilic and hydrophobic, right? Hydrophilic means if you take a glass surface and put a droplet of water, what happens? That spreads on the glass surface, right? But if you take a plastic sheet, you are putting a drop of water, what will happen? That will remain as a droplet, right? Or if you look at the angle of interface between the droplet and the surface, that will be more than 90 degree for the plastic surfaces. And it will be much less than 90 degree for the hydrophilic surface. So that's the hydrophilicity and hydrophobicity. So and then normally when we measure this contact angle for checking hydrophilicity or hydrophobicity, we do it in the ambient condition. But for this application, you need to have this membrane immersed in water, or water will be above it, right? So we immerse that film over here, and we try to put an oil droplet onto it. Okay, then that oil droplet you can see is never touching. I mean, it's never wetting that surface. It's actually repelling the oil droplet. So we have this underwater super oleophobicity. So this is just like the droplet which is placed on a lotus leaf. What will happen to it? It's actually just it will never wet it, like it's just going away. So my LP school, UP school teacher used to say, like, your brains are like lotus leaf. I mean, whatever I'm telling is just, escaping. It's never getting absorbed. So, yeah. Okay, so then what we did was, I think I have a better video here. So we made a oil-water mixture, which is actually a mixture of toluene, and toluene is dyed with methyl red, a orange-colored dye, and then water is mixed with methylene green. Okay, and then this mixture is poured over here, and then it was just kept there for some time. You can see what happens. We are pouring, and the time is shown at the top. Yeah. So it's totally completing, separating with each other, even without application of any pressure. And then we tested, like, if you just keep it like that for hours, it should not mix again, right? So we were able to actually hold it like more than 4 hours. Even after more than 4 hours, it's not coming down. So like, it's very simple. You have an oil-water mixture, take it and then pour through this membrane. Oil is separate and water is separate. So we could use it for oil-water separation, and then there are like some technical parameters about like how much is the flux permeation, some calculation about how efficient this system is. Okay, that's one thing. And then we used it for oil-water separation. Now we tested it for degradation of dyes. So we had this zinc oxide also there. Zinc oxide usually is used for dye degradation due to the photocatalytical properties. Since that zinc oxide was incorporated in this fiber also, we were able to do the dye degradation also. So I'm not going to the details of it. Then yeah, contact angle also I mentioned already. Okay, then one more application we looked for. We took pieces of this membrane and kept it in some bacterial growth media. We could see the inhibition of bacterial growth wherever you have this material. It's again because of the presence of silver doped zinc oxide we used. That silver is actually giving the antibacterial property. That's the major contributor, and zinc oxide to some extent also is contributing to that property. So yeah, in summary, we were able to electrospin a membrane which is having oil water separation application, dye degradation application, and antibacterial property also. Okay, I think I can stop here for now. Thank you very much for your kind attention, and I'd be happy to receive your questions. Thank you, ma'am. Yeah, it's a relatively yeah. Yeah. Yeah, yeah, yeah. Okay, so the entire setup cost us around 5 lakh only. I don't know, I should say it's 5 lakh only, or, you know, it's like water half filled and half empty. No, but actually you can make your own setup also with much lower cost. What you need is syringe pump definitely is required, which can push this polymer solution at a controlled rate. And then DC voltage source, any DC voltage source you can use, but like the voltage usually is in the kilovolt range. So 10 kilo, it's possible. You can make by your own. I mean, if you have a good engineering collaborator, very easily you can make. Yeah. Yeah. Thank you. Yeah. Yeah. So the thing is, like, once you optimize the conditions, if you're doing the experiment for the first time, every now and then you have to see if the process stopped or not. So because this spinning can stop at any moment, because there can be some cluttering of the polymer. The polymer droplet came out, and before it became a fiber, it can actually become solid and block the syringe. That's one thing. And then in that case, you need to see if it is getting deposited or not. So if you just carefully look at the needle, you can see the fiber going out. And if it is stopping, you need to stop and then remove the block and then continue. Because the fiber, you can actually continuously deposit one layer over the other. So for the first time, you should be very careful. And then once you have all the parameters very clearly written down, you can easily reproduce it. Yeah, thank you. Our case, we used polyvinyl pyrrolidone and cellulose acetate. It's a mixture. Yeah. Okay. That also you can take. But I mean, depends on which application you want. This PVP is totally biodegradable. PVA, polyvinyl alcohol, also is highly biodegradable. But like if you want conductive films, etc., you may have to use this PVDF, polyvinyl. I forgot the rest of it. But like depends on which application you want. If it is a electrical application and all, you may not get biodegradable material. But there are a lot of biodegradable film. So when you talk about efficient for what application? I mean, if you want, say, food packaging application, we cannot use a toxic material. You need biodegradable. But if you want like a conductive surface, you don't want biodegradable. You don't want your conductivity to be affected by biological changes, right? So, plastic is good for outside use. Plastic is not good for eating, right? Just like that. Yeah. Thank you, sir. Thank you. Yeah. Yes. Yeah. Yeah. Hmm. Easy to spin. Hmm. Easy to spin. Yeah. 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 Water very difficult to work. Very difficult. Yeah. Hmm. Hmm. PVP and cellulose acetate. Acetate. We commercially purchased it and then used it, and then after the film is formed, from that we removed the acetate to make it hydrophilic. No, no, partly it's remaining. 100% is not possible to remove, and we don't need that much because we just wanted this, hydrophobic to hydrophilic transition. So we are not concerned about how much percentage of cellulose acetate is remaining. We are concerned about how much contact angle is changing. So, hmm. Yes, yes. Yeah, yeah, yeah. Very good question, sir. So there are many works, like now two type of porosities will be there. One is due to this entanglement of polymer fibers, the gap, as I told, gap between the polymer fibers, but this fiber itself can be porous. You can make it porous. So some clever thing other people did is like they incorporated glucose during this process, and glucose also is part of the fiber formed. And after that, this film is taken to hot water. Then what will happen? The polymer is not dissolving, but the glucose is dissolving away. And then you have these individual fibers which are having a secondary pore. And in that way, you can actually increase the porosity. So for adsorption, applications, this is very good. Even our lab started doing something like that. So for heavy metal adsorption, normal films are not very efficient, but when we do this, glucose, sacrificial glucose templated films, you have extra pores within the fiber. That's useful, very useful. Yeah. Yeah, 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 yeah. We can. Yes, people have done it. Yes, yeah, yeah, yeah. Yes. Ah, yes. Oil, water. Yeah, yeah. So we use like 1:1. Yeah. We are not heating, no, sir. This is just a normal mixture. Azeotropic combination is like we are not heating. I mean, we just want a physical separation, no? So, yeah, 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 yeah. Yes, toluene as oil. Just any oil can be used, but as an example, we just took toluene. Most importantly, that the film should not dissolve away. Toluene is not dissolving the film. If in that case, like we were able to keep it for several hours, if toluene is dissolving the fiber, everything will come down together. So the separation should happen, and the film should be stable. It should not undergo any dissolution. Uh, we did not actually see. Our idea is to be applicable for any environmental contamination, right? So if there is, a contamination of water in river, we are not making the contamination. No, it's arbitrarily anything. It can be anything. Yeah, 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 yeah. Oil spilling in sea, oil spilling in lakes, oil spilling in rivers. All this is applicable. Yeah. Thank you, sir. I think, yeah, yes. Yeah, yes, yes, yes. Yeah, so we wanted this photocatalytic dye degradation. For that, zinc oxide was added. And at the same time, we wanted this antibacterial activity. That's why we use silver doped zinc oxide. Based on the function, yes. Yes, yes. it's stable. Like even last year we made this sample, and then now also it's working. Uh-huh. Yeah, strong conditions. For example, if you add sulfuric acid, it will definitely dissolve. Uh, it's just like a cloth. Okay, so cloth, even if it is made up of cotton, due to the thin nature of it and also due to the high surface area, if you use very strong chemicals, you can dissolve it. Strong base and strong acid can dissolve it. But like normal condition, for example, toluene, it's not doing anything to it. We can just keep it like that. Water cannot do anything. Only strongly acidic and strongly basic for my film I'm telling about. There are like, people make ceramic film also through this. They spin it and then do the heat treatment. Then you have a ceramic membrane. Ceramic membrane can withstand acidity and basicity. Acidity basically. Basicity may not be. Yeah, based on the pH response of the material usually. And surface chemistry. Yeah, thank you. Yeah. So pH dependent stability changes could be there. Yeah. So yeah, the technique I was explaining was surface enhanced Raman spectroscopy, SERS. So which is basically some metal nanoparticle deposited on a surface, or if you have a surface of nanostructured morphology, you can use it. Mhm. You mean changing the concentration of the nanoparticle in the film? Mhm. Uh, Limit LOD. Okay. So how to find out the LOD for surface enhanced Raman spectra? You just try different. Keep on do the serial dilution, and then keep on measuring the signal. I mean, basically you need to get a Raman signal for a particular function group. So depending on the concentration, the intensity will go down and down, and then like at some point the peak height is equal to the height of the noise. Then that's your limit of detection. Huh. Yeah, so you have a nanostructured surface which is a solid. Then if your sample is liquid, what you do is you place a droplet of your sample there and dry it. After drying, you take to the Raman. Sirs, there is no different instrument. It's just the regular Raman spectra instrument. Only difference is the substrate onto which your sample is supported. So if you have a SIRS active substrate, it's giving better signal intensity. Yeah, yeah. How much? Voltage. Yeah, that depends on which polymer. So usually it is in the kilovolt range. So our case, I think we use 30 kilovolt DC voltage. So yeah, it's little dangerous also. I mean, you should not touch that and experiment with it. You should stay away from it. And usually, you need to have a closed environment because it should not be affected by the change in humidity. It should not be affected by flow of wind if people are walking around, and also if the floor is vibrating. Some instabilities can be there. So it's better to keep it isolated. So this instrument which we have is yeah, I think I don't have a photograph of it. It's like a closed system and usually kept in a silent place. Yeah. 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 Okay. Book chapter. Okay. I did not write. My student wrote. Uh-huh. Mhm. Mhm. So basically, magnetic quantum dot, how it is made, it is you make the semiconductor quantum dot, and then you dope some magnetic materials, usually some transition metals, which are paramagnetic in nature. So at the same time, you have this fluorescence property and magnetic property. So if you want to say detect an analyte and then selectively separate it, this can be used because this material will be responsive to the external magnetic field, because like this is moving and attaching to an analyte, and then you are actually applying the magnetic field. So whichever is attached to this analyte is coming and getting deposited near to the magnetic field, right? So you have this multiplex functionality of detection and separation in the same material. This is the idea. Yeah. I'm very happy that a lot of questions are coming. That means like see, only two type of people will have questions, right? One is like I mean, only two type of people won't have questions, will not have questions. One is people who understood everything, and other people who did not understand anything. But like you are in between. That is the right place for a scientist to be. I mean, you should not think like everything is understood. There is something remaining. Please, please. I think the mic is not working, sir. You can be loud. I will hear. I think. I took extra.
Sir, how does the size and the shape of silver
Hmm.
nanoparticle as antibacterial efficiency?
Okay. So I'm not a biologist. So what I know is the antibacterial activity depends on the cell permeability. If the nanoparticles can enter into the cell membrane or not. So cell membrane also is like a fibrous membrane where you have this vesicle type of structure. This amphiphilic molecules, lipid molecules, are oriented in such a way that hydrophilic part is outside, and then another layer of hydrophilic is in the pointing inside. So it's a double layer. So not every nanoparticle can penetrate to that. So the penetration of the nanoparticle through the cell membrane depends on the size of the particle and also shape of the particle. So that's why certain nanoparticles are able to enter into the cell that can kill the cell. But if it cannot enter the cell, it will not. So that's why there is a optimum size required for the penetration, and this is my understanding. There may be more things to that, but this is the most rudimentary explanation for that. Did I answer your question? Okay. Okay, thank you. Okay. Thank you very much.
this is the last lecture. Tomorrow we have another lecture that will be questions, if you have. But this is really a sort of summary of what we talked about. Not exactly a summary of the material, but summary of the concept. And we're also going to talk about the future. Now, it is very difficult to talk about the future. Sometimes we can think of things that happen, and then from today till tomorrow, the world is changing, your life is changing, the perceptions are changing. So we're going to talk about the future, but we can meet again in 10 years and see if what we thought will happen will really happen. So what we will talk about, we will start with the discussion a little bit of the current perception of nanotechnology and the environment. What people think about nanotechnology and the relationship with the environment. Then we will pose the important question, is nanotechnology our future, our hope? Or maybe nanotechnology will destroy the environment even more? It's a very big question. The answer probably is somewhere in the middle, but this is important to talk about it. And then we will talk a little bit about future trends. This is sort of a poll that people made about if nanotechnology is good or bad. What do you think? What do you think when people say nanotechnology? Do you think, I don't know, maybe after this course, maybe without connection to this course? I'm interested to know, when the word nanotechnology is mentioned, do you think this is something good? This is something good for the environment, or this is something bad? Let's hear you. Who thinks that nanotechnology is good? One person, two people, 3, 4. Who think that nanotechnology is bad? Well, we don't like to think bad thoughts. No, okay. So actually, this question is really a very important question, even for the future of nanotechnology research. Because if we, as chemists, can convince the country, can convince the public, can convince the government that nanotechnology is good and is going to do good for the world and the country, then we can hope that the government will support us doing our research. That the people that are not at the university going to give us salaries and funding for helping their lives. So actually it's very important, if we think of the future, to really try to use nanotechnology for good purposes, for good things, for good developments in the world. There's actually a lot of work on nanotechnology, not just the chemistry or the engineering or the biology, but also the ethics. Is it a good thing to start playing with small atoms and molecules and make new materials? Because you know there's also some negative aspects, as we talked about earlier, that maybe going to such a small dimension can hurt our body, because the nanoparticles, as we saw in one of the first lecture, they can go into our brain, they can hurt our health, they can damage our water and the environment. So there is a lot of discussion, ethical discussion in philosophy, in social science, about the benefits and the harm of nanotechnology. You know, we talked about the good things and bad things about nanotechnology in our first lecture, and this is actually, I think it's a very representative slide that shows the two parts of nanotechnology and how people perceive nanotechnology. On the one hand, we have all the environmental pollution and damage because of nanotechnology, because of industries that use nanotechnologies to make new materials, to use nanotechnology to generate new energy sources. All this is causing pollution. This is the bad thing. But also, if you think about it, there is a lot, and we talked about it, a lot that nanotechnology can do to help with cleaning this pollution. And this is something that we always need to remember. If there's bad things that nanotechnology does to the world, we need to use the same nanotechnology to offer solutions. This is actually the main power of science in general. Science can be used for bad things, but science and us as scientists can do good things. It's all a matter of choice. Actually, this is something that I took from a article about nanotechnology in India. What are the activities that nanotechnology takes place in this big country? And you can actually see a lot of activities that can be described as nanotechnology. Even sports, even food. You know, remember we talked about the carbon dots? Carbon dots are everywhere, including in our foods. There's a lot of nanoparticles in our food. I don't know if it's good or bad, but it is there. Medicine, cosmetics, detergents, pesticides, electrical appliances, of course. So nanotechnology is everywhere. And the risks and the benefits of nanotechnology are everywhere in all these broad fields. So if people ask you in the future, okay, so what nanotechnology actually does for us? Maybe this is something that you learn in your chemistry courses. You have this lecturer coming from overseas and gives you 1 week of lectures, but maybe it's not related to our real life. That's not true. And this is actually something that very important that people will know, because these things, the whole spectrum of activities and contributions of nanotechnology, this determines the perception of people about nanotechnology. It's not something abstract, it is something real. For example, did you know that nanotechnology is also in our clothes, in textiles? I actually didn't know until I started working on this and reading about this. So textile, our clothes, we have nanotechnology there, okay? We have nanotechnology in developing clothes which are wrinkle resistant using nanomaterials. We can strengthen clothes using nanomaterials. We can block UV light, which is very important to prevent cancer to the skin and old age for the skin, just using nanomaterials. Sunscreen is made of nanoparticles. Computing, of course, antibacterial clothes and surfaces and other things that are all nanotechnology. So the message of this lecture is actually you can see in this slide. This is a representative picture of what we and the people in general can think and do about nanotechnologies. We have the toxicity. PNEC and PCR are just polymer, some plastics that make nanoparticles. They can be toxicity, but then there can be benefits. Now let's think about future trends. What the future holds for nanotechnology and the impact of nanotechnology on our lives. Here, these are the top 9 trends in nanotechnology based on a poll. There was some website, I think it was in Science or Nature, that scientists from all over the world, scientists, could answer what are the future trends of nanotechnology. And this is the list. It's actually a very interesting list. Some of the topics, we talked about it in this course. Carbon nanomaterials, semiconductor nanodevices, green nanotechnology, nanocomposite, material that have different nanostructures that together make good and new materials. Nanosensors, we talked about it in this class. Nanofilms, which can have different applications. Nanoencapsulation, mostly in medicine, in encapsulating drugs in nanocapsules and using them for drug development. Of course, energy nanomaterials, we saw it's a very big and important field, and computational nanotechnologies. Now, here we can see one direction which I think holds a lot of promise for nanotechnology. You know, the world generates so much waste. Lots of plastic waste, lots of waste in water, lots of waste in the air, trash, contamination, pollution. The problem of waste is already one of the major environmental problems in the world these days. It can simply swallow us on the way, all the waste and pollution generated by waste. I think that nanotechnology gonna be a main solution for dealing with waste. In some lectures this week, we talked about this. We talked about how carbon dioxide can destroy organic pollutants. We talked about metal nanoparticles cleaning water. I think that this direction, this trend, will be a very important activity for the future. And maybe you will do that. Maybe you will work on nanotechnology for waste disposal and for overcoming the waste problem. There will be a lot of nanotechnology applications, new nanotechnology applications in industry. There might be even new industries starting from nanotechnology and nanomaterials. For example, cars. New cars now There's many cars that are electrical. Electrical cars need better batteries, stronger batteries. Here, nanotechnology can really play a major role, developing new technologies for batteries. Information technology. We need stronger and stronger computing power. For example, for development of artificial intelligence. In order to do that, we need smaller and smaller electrical circuits, electronic circuits. Nanotechnology will make a big impact in this field. It already does. It will be even more prominent and more active in the future. Make a very important contribution here as well. As we said, remediation of pollution, sensing and monitoring heat, pollution, CO2 generation from various sources and other gases, biofuels and alternative energy. Biofuels and alternative energy all are involved, or in all these fields, nanotechnology is very important. Let's talk a little bit about the future, or possibility for the future, for positive and negative impacts of environmental of nanotechnology on the environment. Actually, this slide could be the first slide in this course. We need to remember that nanomaterials are not only man-made. You know, volcanoes, for example, fires, they all occur naturally and they generate nanomaterials and nanoparticles. These nanomaterials can go to the water, to the air, and to the soil. They can cause us health problems. But if we learn how to deal with them and how to use these for good benefits and not bad, we're going to be in good shape. Of course, the pollution is a big problem. That's the negative part of nanotechnology. But let's finish with the positive part of nanotechnology and its possible contribution. Nanotechnology can really help us solve many problems in the world these days. Okay? Here this shows solutions for water, but if you think about it, nanotechnology can be used in all different aspects, in all different challenges that the world is facing. So let's be hopeful, and I hope that you will take it and make the world a better place using nanotechnology or anything else. And thank you.
Thank you, Professor, for this nice insights for future perspectives for the nanotechnology field. Any question from the audience side?
Thank you, sir, for your lecture. Sir, while discussing the future trends of nanotechnology, you talked about...
I see it that all these things, all the calculations and algorithms and artificial intelligence, all if they're used smartly, they can really help in developing new technologies and new solutions using nanotechnology to help the world.
Okay, sir. Sir, one more question, sir.
Sure.
Sir, what is the future aspects of scaling these lab-based experiments to an industrial scale, or how can we scale it, or what are the
Look, in general, regardless of nanotechnology, to scale up processes and technologies that you develop in the lab and to go to industrial scale is not an easy thing. This is something, you have, in many cases, things that work great in the lab, but if you try to do ups
Have made us to understand much more this nanotechnology and applications of these nanomaterials, right? So I would say, like after your slide, it's like we can't say like nano against nano,
I'm sorry?
nano against nano.
It's a great way to describe it. Yeah. It's just like in China there is this yin and yang. So this is it. Like everything. Love and hate.
So one of our students, she is little hesitate actually to, she has a good question. Like
Okay.
we have learned that there is lots of use of nanomaterials in chemistry, in medicine, mainly in medicines, and she wants to have your view, the use of, what's the use of nanotechnology in biotechnology, from your side.
Well, in biotechnology, in many cases, you need to design small chemical systems that will help biology. For example, a good example is an interesting, relevant system is that people want to do genetic engineering or to cure genetic disease. The way you do it, you need to take DNA and bring it into the cell so it will fix the bad DNA in a genetic disease, for example. So there is an activity about designing a chemical cage, just like we heard yesterday, that can carry DNA through our mouth or through our blood and take it to the cell and then inject the DNA into the cell. This is nanotechnology. To design the vehicle, the drug delivery. Exactly. So this is just one example of how nanotechnology can help biotechnology. There are many other examples.
Yes, sir. Just in your support, I would like to add, so perhaps Pansu was asking about computation. I think, sir, this application integrated circuit, ultra pure silicon, that goes on nano level.
Yes, of course.
So that is the direct application, modern technology. The fabrication part nowadays, the size of the chip is reducing, but the number of integrated circuit is increasing. So that is because of the application part of the nanotechnology. I think nanolithography, is it?
Nanolithography is a very important technique to make circuits, nanocircuits, integrated circuits.
About the computational chemistry, like if you use some DFT density functional theory or some other scientific software to calculate the electron density to find out the structure of the nanomaterial, there are some models. So there also the peoples are using some model to know the structure and function of the nanomaterial. These two are the major burning area, one of the major burning areas regarding the computational research in nanoscience and nanotechnology. Am I correct, sir?
Yes, that's of
That's
course
what
one.
that way it is there. Okay.
Well, we don't want you to go away from this side, so we can have more and more discussion. Just a small query,
like we know people are dying because of heavy pollutions, pollutants, right? Nowadays we talked about this like microplastics, right? If someone is, you know, severely affected by microplastics, so is there any data that how much microplastic we are consuming? Or
Yes, actually, there are lots of research which are actually very scary because the research found that over the years there's a lot of plastics accumulating in our cells, in our brains, in our lungs. People don't know exactly what they do in the body. If it's bad, if it's very bad, maybe little bad. But the fact is that microplastic is everywhere. We eat it in our fish, even vegetables. We breathe it and it goes into our body. That's a big problem. Maybe over the years we will find that some diseases are related to microplastics.
later on?
Maybe. But definitely we know that it is a problem. We know that this is a health issue.
So everything might be using or eating contaminated with microplastic, whether the water or
Not everything, but many things.
thank you. Thank you.
I think no more questions from the audience side. So we shall thank to Professor Raj. Yes, one more question, sir. Sir, I want to know that there is a technique which we can find out that the person is affected from the drugs or the alcohol as a is a major problem. So in a nanoparticles and something which show that or which tell us that the or the person is affected from drugs or alcohol in major amount.
Well, this is a chemistry research or biology research. I don't see the connection with nanotechnology, what you're asking, or maybe I missed your question. But to find out about alcohol or drugs, this is a biology or biochemistry research, but I don't see the connection to nanotechnology.
Okay, she is asking the extent of, suppose we are seeing, we are looking at the drug use,
Okay.
or a person is there who takes regularly the drugs.
Okay.
So, is there any technique or method to know at what extent they are habitual to the drugs or alcohol?
There are techniques that can measure drugs in our blood, for example. Some of these techniques are related to nanotechnology, but some of these techniques are just chemistry techniques. But it is possible to actually now diagnose drug uptake and drug abuse and alcohol using various very nice and very interesting systems.
Stop drug abuse using these techniques. Drug abuse.
I don't know if you can use nanotechnology to stop drug abuse, but you can use chemistry and you can use psychology.
Okay. Thank you, Professor. Yes, one more question. Okay.
So first of all, thank you, sir. Your lectures are very, very interesting. Sir, my question is that if you want to suggest an experiment to us in master's level that we can perform related to nanotechnology.
Um, Look, experiments you can do. You need to find good question first. I think one thing in my research is, for example, these carbon dots. They're easy to make. So if you can make carbon dots, you can use them for many types of experiments. and this is actually an advice I would give you, try to find good way, an easy way, relatively speaking, to answer important questions. You need to think. It's not easy. It's not something that comes out every day. But if you think of good technique and good questions, you integrate them together, you can have good experiments and good project for master and good paper.
Any more questions? Sir, thank you for all your lecture. Can we have get your all slides, all PowerPoint presentation?
Yeah, I can give to Professor Patra or whoever. Sure, yeah, yeah. I can send them to you and no problem. You can use them. Sure.
We have shared the YouTube link, I think, group also.
And watch it again and again to have better understanding, right, about this nanotechnology, what Professor Raj has explained, all continuously for 4 5 days, right? And we will have also the material, the content, okay, for all of you. Thank you.
I think now I should conclude this session, morning session. And thanks,
Thank
Professor
you.
Raj, for
Thank
this
you.
nice interaction with your students also. Now the break for the lunch, and after the lunch, the next session will be started.
materials, then various devices. Various devices. These materials are often developed through advances in material science, physics, and chemistry. Chemistry and including areas of photovoltaic, energy storage, and thermoelectrics. This energy efficient lighting also. Thermoelectrics, Rambabu is going to talk after me. He is theoretical. So these are the applications of emerging materials. These are advanced materials. So they are used in energy storage, energy conversion, energy harvesting, and hydrogen storage also. Most of Assis Singh and other people are working in this field, senior Assis Singh. So these are the definitions for students actually. What is battery? Then we have primary batteries, secondary batteries, then cathode and anode. Everyone knows it. Chemistry people. So this is also when we are using. Then we are using. We will go for a number of times this active mass. Active mass, then this electrolytes, separators, fuel cells, electrochemical capacitors, ultra capacitors, and EDCL that I will introduce later on. Then this is a term used open circuit voltage when we are going to fabricate a device and characterize that device. So these terms are coming: closed circuits voltage, the internal resistance, Faraday constant that is used for number calculation, thermal runaway when it goes to a particular stage. So electrochemical conversion devices are pervasive in daily life. Batteries, fuel cells, supercapacitors belongs to the same family of energy conversion devices. They are all based on fundamentals of electrochemical, thermodynamics, and kinetics. More chemistry is all three are needed to service the wide energy requirements of various devices and systems. Then supercapacitors are considered as an alternative to batteries and fuel cell. So just charge storage ability of a supercapacitor mainly depends on a specific surface area, pore structure, electrical conductivity, and charge transfer capacity of electrode material, how this charge transfer takes place. The performance of supercapacitor depends on nature and microstructure of electrode material. Professor started talking about electrolytes. So he modified the electrolyte for supercapacitor applications. We are still working on electrode materials. So this is a diagram that is called the Ragon plot. So you can see these are the conventional capacitor. Capacitors, then we have fuel cells, which has a specific energy very high, and conventional capacitors, they have a specific power. That one is very high. So capacitors are supercapacitors are in between these two devices. This is supercapacitor. Then there are various types of supercapacitors, then components of supercapacitors, commercial supercapacitors, and applications of these superconductors. So this is three types of supercapacitors. First one is called as electric double layer capacitors. Second one is pseudo capacitors, and hybrid is in between these two. Both mechanisms are used. So you can see बोर्ड पे नहीं आ रहा है लाइट देखो ऊपर इसमें आ रहा है बोर्ड पे नहीं आ रहा है ऐसा नहीं दिखेगी आएगी so this is first one is electric double layer capacitors. So you can see that at anode and cathode there is formation of double layer, and capacity of this one is increasing because of that these two layers. In case of these pseudo capacitors, there are this one is anode and cathode. So these cations are these solvent molecules. They form a group of material, and this will increase the capacity of capacitor. So and this one is hybrid. That one is mix of these two. So energy storage mechanism for these three devices in electric double layer capacitors. Capacitance is originated from the accumulation of charges at the electrode. Both electrodes, electrode and electrolyte interface. Therefore, controlling the specific surface area and pore size and enhancing the electrical conductivity these are the methods for increasing the capacity of a supercapacitor. Then energy storage of this pseudo-capacitance is realized through the transferring this Faradic charge between the electrolyte and electrode due to reversible multi-electron redox Faradic reactions. Chemistry pool, they are more knowledgeable than me in this case. Then this energy storage in this one realized with the electrolyte and electrode due to reversible multi-electron redox Faradic reactions, which generally exhibit the high specific capacitance and energy density compared to first one. This is for mechanism of how these charges are in second one. So if you see these supercapacitors, then this is battery and this one is fuel cell example. So if you see the value of this energy storage devices and energy density and power density, because these two terms are very important in case of supercapacitors. So if you take a film capacitor, then this value of energy density is 10 to the minus 2 to 10 to the minus 1 watt hour per kg. If you take capacitors, that is conventional capacitors where there are two parallel plates and in between you have dielectric material, then this one is less than 0.1 watt hour. This unit is energy density watt hour per kg. Sometimes this is called as grammetric density also, because this depends on mass. And second one is called as volumetric, this depends on. So you can see in case of supercapacitor, this value is 10 to the minus 1 to 10 to the plus 3, and this power density is also very high. That is in between these two devices. So this is just a comparison between these devices. So this is the difference in mechanism, what I have told you, how these charges are stored. If you take charge storage mechanism, then this here it is electrostatic, means charges are attracted because of their opposite nature of charge. Then this double EDSE, this one is non-Faradic, and materials used for this electrode are activated carbon, graphene, reduced graphene, CNT, and carbon aerogels. Then in case of pseudocapacitor, we have reactions like redox reaction, under potential deposition, intercalation, electrochemical, that charge storage mechanism is electrochemical. Then this is Faradic, and these are the materials which are used as a electrode in this. That is transition metal oxide, especially MnO2WO3. Then conducting polymers also used as a electrode. In case of hydrogen, that is a mix of both. So when you have a electrode material, so you have to characterize that one so that you can compare the properties with others. So there are electrochemical parameters which governs the performance of supercapacitor devices. One is cyclic voltammetry, CV. Then we have electrochemical impedance spectroscopy, and this galvanometric charge discharge cycle. These are the three parameters. So if you are going to prepare a synthesize a electrode material, then you have to go for these three properties at least, so that you can say how this material is. So this is cyclic voltammetry, CV. Chemistry, you have 2-3 setup also, 2 or 3. So in this case, this is used for this number of parameters you can realize through this CV measurement, cyclic voltammetry. Actually, in cyclic voltammetry, we are plotting current versus voltage, and that nature of that relation between these two, that will depict the type of this supercapacitor. So this is the equation is used for calculation of specific capacitance. Yeah, that one is farad per gram, and actually you plot IV curve, then the area under the curve, that one is IDV. This K is scanning rate, yeah, that is called as scan rate hai, that is millivolt per second, where m is mass of the active electrode, that is active mass. Then from this we can calculate the specific capacitance. Then this is the, for these 3 type of electrodes, if you have EDLC, first one, yeah, this one is for ideal actually, ideal supercapacitor, this one is for pseudo capacitors, and the last one is for non-ideal capacitors. So the second parameter that one used to characterize this electrode materials, that is galvanostatic charge discharge cycle actually. So this is various, how much cycles that material can go for charging and discharging process, this is used for that one. Then this is the CV curve for IV current versus voltage. This is for different type of electrodes. You apply different type of electrodes, then you will get this type of curves. Then this is IV dependence. So that depends on, I have written this I is equal to A V power B. Value of V will differentiate between these 3. So in first case, when you have EDLC, then this B is 1. B is 1. If value of V is approximately equal to 1, then that will be for this GCD, and third one is for battery type of materials. So this is the, now this is electrochemical impedance. We can find out from this one. So impedance means contribution of different parts, different circuit elements, that is resistance, capacitance, or inductor also, then we call it combination of the 3 is impedance. So in this material actually, when you are going to measure the property of this one, so suppose you are using electrode, then bulk property and grain, that can be, we can find out from this. This in physics this is called as Cole plot. So from this one you can find out the contribution of bulk material, grain boundary and grains. So this is an important technique to find out the resistance impedance of material. This is the equivalent circuit of this one for this particular case. So if you have a super capacitor, then components are separator, collector, electrodes and electrolyte. So this one I have shown in figure. This is collector in those both sides, the collecting current. Then you have electrolyte, separator, and anion cations, they are moving through that one, and this red color is electrode. So this is just about, this is not so important. So if you go for electrode materials, then for electrode fabrication actually, so commonly used electrode materials are activated carbon, graphene, then carbon, because it is very easy to fabricate these materials. So these materials we are using to improve the property of supercapacitor. So this is again supercapacitor, different type of electrodes and their actual comparison. So this supercapacitor, we use this structure, compositional flexibility and inherent oxygen vacancy. Perovskite structures have attracted wide attention for the promising electrode materials. These are the property of perovskite materials. And perovskite materials means formula is ABO3, where A and B are cations and O is oxygen. I will give you later on this structure. So in this perovskite structure, that ABO3 structure, you can have different type of doping to improve the property of that materials. Then you have this double perovskites, you have this iron non-stoichiometric compounds you have. These are the different form of perovskites which we can play with different doping and processing parameters. This is perovskite materials, they have different uses in different fields. Challenges and for, towards the electrochemical supercapacitors. These are some important advantages of this supercapacitor, and which is more favorable comparison to other electrodes. These already students know that top to bottom and bottom top. These are methods for synthesis of nanomaterials. So, in case of supercapacitors, this power density indicates how fast a device can deliver the energy. Whatever energy is stored, how fast you can deliver that energy, that is governed by power density of supercapacitor. Then whereas you have energy density, that indicates how long an energy storage device can be used. That is the life of that one. So supercapacitors can outperform batteries in specific energy density and power density by many orders of magnitude. I have shown in Ragon plot. So these materials are versatile energy storage material. So before that, there are number of methods for synthesis of ferrites. We have used with this Nilan Sahu is my MSc students. He used a green method to synthesize these ferrites. So this presentation analyzes state of art of energy storage technology and all these things that are like. So this is about perovskite structure. I have told you the structure is ABO3, yeah, X actually. So perovskites are also used for in solar cell material and other applications. Then ferrites, that one is similar to that is perovskites, but this formula is AB2O4, where V is iron Fe3+. So in the case of spinels, actually, these materials are oxide materials, so they have very high resistance. And in this case, if you take one unit cell, then there are 8 molecules. Total, you have 56 ions in one unit cell. Out of that, 32 oxygen. They are closely packed oxygen atoms. And in that cubic structure, you have 64 tetrahedral sites and 32 octahedral sites. Octahedral size, wide size is comparatively more than tetrahedral size. So these two cations in spinel structure, A and B. B is iron actually, Fe3+, and A is divalent. So if these divalent ions, if they are going to tetrahedral side, and this trivalent ions, they are going to octahedral side, then that one is called as normal spinel. But if divalent ions going to octahedral side, and half of the trivalent ions, they are coming to this tetrahedral side, then that one is called as inverse spinel. So these spinels are important, but generally people are using mixed one, means normal and inverse spinel. So these physical properties are interest to material science among the perovskites, including superconductor. These are the different uses. When they are used in solar cell, in efficiency you have get that in more than 26%. This is again about ferrites, what I have told you. A is divalent, that can be magnesium, manganese, cobalt, zinc, nickel, all these things. So by this green method, we have prepared this zinc cobaltite. These are spinel materials. So these are number of advantages. So for this, we have used solution combustion method. In combustion method, there are different type of methods. So we have solution combustion method. So we have used in this case, this is called as green, because we have used the flower extract. This flower is available in our campus, that is called as Hindi Palas. And Palas, so we have collected that flower of Palas, then we have dried it outside for 1 or 2 days, then we have washed it, then again we have dried it, and then we have taken this extract from that one. And that extract is used as a fuel. In combustion method, people are using a number of materials like urea and citric acid, all these things. So we have not used any of these things. We have used only extract of this flower. So that is why this is called as green method, and number of people are working on this one. So these are the how they have collected this flower extract, flower and made their extract. So in this case, first we have collected flower, and after cleaning, we have prepared the extract from that flower, and using extract to synthesize zinc ferrite by Sol-Gel method. So we have used that one in place of citric acid or in place of urea. So this is the Palas is called as Palas flower, is already available in our campus. So we have collected from more than 3-4 kg of this one, and then we have dried it. Then we have made the powder of that one, and for that powder, of some fixed time, we have taken the extract of that one. So in this case, he has collected 2.5 kg of flour, and then it was washed, and number of times dried and washed. Then we have made the powder of this one, and that from powder we have collected the extract. So this is the dry flour, and these are the powder of the flour. Then we have used in a beaker distilled water, double distilled water, and then the powder of that flour. And then we have used for at 18 degree for 1 hour, and that one we have kept in fridge. Whenever we are using, then we are taking it from fridge, not is at room temperature. So these are the different stages that students they have done. So this is the extract of flour. In this case, we have taken constituents in nitrate form, that is zinc nitrate, then cobalt nitrate in stoichiometric ratio, so that we can get exact spinel by using weighing machine. Then this one kept at 50 degree, and after 42 minutes approximately, we have calculated this one, how long we can keep it. So after this you can see this is the doing process of this synthesis by using combustion method. So there is internal energy. By that, this will come as a soft mass, and then we powdered it, and this one is now the material that is ferrite. So this is the powder form of ferrite. So based on this one, actually I have not used this one. There was a separate story for that one. We have not measured that one. So in another system, that is zinc ferrite doped with lanthanum. This one we have used as a electrode. So this one we have prepared. That is my research scholar Apurva Rai. She prepared, and this is published in Energy Storage 2-3 months back. So these are the XRD pattern. You can say this is very clean and material is found. This is the ritual analysis that we have predicted the structure, and these are the parameters, because this lanthanum is substituted at iron oxide, ferric side. Then these are the different composition depending on the value of L, and then we have calculated lattice parameter. Then using Debye-Serre method, we have calculated the particle size. Then we have used Williamson-Hall method to find out the strain and particle size. Then we have also used calculated this X-ray density, and these are the hopping length. This is not used in this one. So these are the different control parameters for these 4 samples. This one is distribution of particle size. This is the TM image of that powder, and these are the CV curves, which I have told you that in ideal case you will get a rectangular type. So we have obtained this type of for different compositions. They have almost similar behavior, and then we have compared this value with other published research work, and we have found that our value is almost comparable to the reported values, and better than some of the reported values. This is the scan rate versus specific capacitance, how it is varying, because this is important for application point of view. And this is the equivalent circuit. So from this work actually, we have, for this paperwork, we have synthesized material by auto combustion synthesis, where successfully synthesized pure and lanthanum doped. This is not doped, actually substituted, but in chemistry pool they are using doped. So this is lanthanum doped zinc ferrite for application as electrode material in supercapacitors. The detailed analysis confirms the formation of cubic structure without any secondary phase, because the XRD pattern was very clean. The incorporation of lanthanum into zinc ferrite enhances the electrochemical performance and capacitance when utilized as a supercapacitor electrode. We have used electrolyte, that is KOH. So lanthanum doped electrodes exhibit superior electrochemical properties, and finding this suggests that this lanthanum doped zinc ferrite holds promise as a high performance supercapacitor electrode materials. This is only better than others. So 4 years of our vice chancellor. So university has developed like anything. We have gone from B+ to A++, and number 1 is UGC listing, where we can start our own courses without any permission from other agencies. So thank you all.
Thank you, sir, for nice lecture. Now session is open for discussion. If you have any queries, please ask.
यहाँ नहीं पूछ सकते तो बाहर पूछ लेना लेकिन पूछना जरूर. ये बहुत इंटरेस्टिंग है. You can take every type of flowers and you can synthesize these ferrites.
Anyone have any question? If there is no any question, then can calculate.
अच्छा है. Green, because we are not using chemicals and other things. No chemicals. No chemicals. We are using some chemicals, but we are not using harmful chemicals. For that, we have used this extract of this flower. Number of properties will improve when you use this green synthesis. Particle size, distribution of particle size, uniform. And XRD is also very good. If you use citric acid, then the XRD, there are number of small this impurity peaks are also there. In case of lanthanum doped, I have is plus and 3-4 other flowers also. I will tell you, then other people will start doing that one. So once it is, it will depends on type of flower also. But this one is very concentrated, so we have used very small amount. That it is not that this much amount we have used and we have got it. We have varied this volume of this extract. Then we have seen the process and which one is the best. That one we have reported. Particle size is less than 100 nanometer. The same, we have not gone for same, but most of the particles are spherical. I have shown you the TEM image. Thank you, thank you.
Thank you, sir.
अरे मेरा मीटिंग है वहाँ.
अब 1 घंटा बोला, मुझे 1.5 घंटा करके कहाँ से दे रहे हैं?
एकदम ज़्यादा बोल सकते हैं.
कहाँ है स्लाइड्स कहाँ हैं?
Dr. Ram Babu did his MSc
Thank you,
from
sir.
University of Hyderabad and MTech from IT Delhi.
Thank you,
Then
sir.
he completed his PhD
अच्छा
from IT Hyderabad.
पॉइंट. So ये up है ना, up है ना?
Dr. Ram Babu has published more than 23 papers in national and
Thank you.
international scientific journals. His research interest is spintronics, material magnetism, topological materials, thermoelectric materials, and superconductivity by using density functional theory simulation. Okay, sir. Please, I would like to invite Dr. Ram Babu.
Thank you, sir, for the nice introduction. Can you hear me? So firstly, I thank the organizers for giving me this opportunity. So I am going to present study of the thermoelectric transport properties of gentle phase nitride Ca2ZnN2, a first principles approach. So I want to know how many of you are familiar with simulations in this class? Okay, one person. Any simulations, molecular dynamics or density functional theory? Okay, so yeah. So the outline of my talk goes like this. In the first part, I will discuss the brief introduction about the density functional theory, and in the second part, I will discuss some of the results that I have obtained for this compound Ca2ZnN2. So firstly, I will talk about why simulations are necessary. Then I talk what is quantum many body problem. Then what are the problems associated with many body problem. Then I go to Born-Oppenheimer approximation, and what is that approximation. Then what are the shortcomings in the Born-Oppenheimer approximation. Then what is Hartree method and its limitations. Then what is Hartree-Fock method and what are the limitations of the Hartree-Fock method, what are the complications involved. Then I will go to density functional theory, a brief introduction to the density functional theory, how it is overcoming the difficulties of the previous methods compared to the present method. Then I will talk about Kohn-Sham equation, some LDA GGA methods. Then I will discuss the results. So why simulations are necessary? Many times we are doing experiments, some people are doing theory and some people are doing simulation. So what is the correlation between theory, simulations and experiments? Suppose we are doing some experiment and we got you are expecting some physical properties or some chemical properties, and after measuring you are not getting the desired properties. The quality of the properties may be low, we do not know exactly. By using simulations, we can predict in advance how much gain or whatever, any physical property, how much we are going to get, that we can predict through the first principles calculations. Then we can compare it with the experiments also. We can do other way around also. First we can do experiment and we can try to prove it with the simulation, or first we can do simulation and we can say that yeah, this compound is going to have this much, some parameters, some properties, so we can go for the experiment. That also we can do. So in that case we have to do simulation, and many times what we do, suppose we do some experiment and the experiment involves costly chemicals, and after preparing the sample, what we do, we will measure and you are not getting the desired property, then the sample is a whole waste. So in advance what we can do, we can predict physical properties or chemical property, anything, any property, any property, whatever we are measuring with experiments, that can be done with simulation. So we can do simulations and we can tell that yeah, you are going to get this nice property, so you can go with the experiments. That also can be done. So as I told you, there are different ways to study the condensed matter. One is computation, one is experiment, and another one is theory. So we have all correlations among these three. So now I come to many body problem. So what is many body problem? We know Schrodinger equation. Schrodinger has given this time dependent and independent Schrodinger equation in 1925, and which gives us H psi equal to E psi. What is H? H is the Hamiltonian of the system, which is nothing but kinetic energy plus potential energy. And yeah, it is not coming here. Yeah. Okay. So here we need to know the Hamiltonian of the system. Once if you know the Hamiltonian, you can substitute that Hamiltonian back into the Schrodinger equation and you can solve it. And is it true in all cases? Can we solve the Schrodinger equation for all cases? That we have to think. Yeah. So if you go to many body problem, suppose I am talking about one electron system. So what is one electron system? We know in hydrogen how many electrons are there? One electron is there. So for one electron, when you try to solve the hydrogen atom by hand, also we have solved in gradation. So if you solve hydrogen atom for one hydrogen atom, it is having only one electron. So for one electron, how many variables we are getting? We are going to solve that hydrogen atom problem by using Schrodinger equation by variable separable method, where we have taken the total wave function as the product of r into some YL m theta phi. So r theta phi we have taken, right? So we have three variables, radial part and theta and phi. So you need to solve for three variables for one electron system. Then we have done some derivation, and after 20-30 pages derivation, we are using many approximations. There we some legendary polynomials, associated legendary polynomials, associated log array polynomials are also associated with that. And after doing some 20-30 page derivation, we are getting some ground state wave function in terms of theta ylm theta phi into some r part, right. So, this is applicable for one hydrogen atom system, but what if we go to more than one electron systems? Can we apply the Schrodinger equation to solve the for more than one electron system? For example, if you go to helium is having 2 electrons in its atom, right. So, for 2 electrons, how many variables are required? For 1 electron, we need 3 variables, right. For helium, 2 electrons, we need 6 variables, and if you try to solve by hand, theoretically, you cannot solve. Some people might have reported, but people do not believe that, right. So, for 6 variables, second order differential equation, which is Schrodinger equation, is second order differential equation, solving is very difficult. You keep on solving, you never get the solution. So, fortunately, we have Schrodinger equation. On the other hand, unfortunately, we cannot solve it for 2 electrons. 1 electron we have solved, but for 2 electrons, we have the equation, we have second order differential equation, but we cannot solve. So, what to do? So, this is about 2 electrons, but in real life, we are dealing with real systems. Suppose somebody is working on zinc oxide, somebody is working on LaMnO3, somebody is working on some big molecules, where this molecule is having 100 electrons. If you are having 100 electrons, 100 into 3, how many variables are coming? So, can you solve it? It is impossible. Nobody can solve. So, such kind of problem is known as many body problem. So, there is a problem, right. So, many body problem, many body means there are many electrons present in the system. So, that is what I have written here. So, for many body system, suppose I am having m number of nuclei and n number of electrons. So, in that case, I have to find the Hamiltonian. As I told you, H psi equal to E psi is the Schrodinger equation, where H is kinetic energy part and all these 3 terms are interaction terms, which are known as potential energy terms. So, for n number of electrons, I can write this one as, this is sum of the kinetic nuclear kinetic energy, electron kinetic energy, and this is the electron nuclear interaction, electron interaction, and this is nuclear interaction. So, the same I am writing here. The total Hamiltonian is nuclear kinetic energy, electron kinetic energy, electron nuclear interaction, electron interaction, and this one is nuclear interaction. So, this is the Hamiltonian. Once if you know the Hamiltonian, you may substitute that into this Schrodinger equation and you will get the solution, but we are not getting the solution unfortunately for many body system. So, such kind of problem is known as many body problem, because we are getting for n electrons, we are getting 3n variables. So, we cannot solve 3n variables. Okay. 6 into 6, 6 into 36. So, 1 into 6, 36 plus 6, 42 number of electrons are there in this system. Okay. So, we have 42 number of electrons in benzene system. So, I want to solve this benzene ground state wave function or ground state energy by using the many body problem or Schrodinger equation. So, is it possible? It may be possible if you use the variational principle. So, variational principle we have to use. By using the variational principle, we can solve the ground state wave function of the benzene. So, how to do that? Let us try to see. So, as I already told, since we have 42 number of electrons, for 42 number of electrons, how many coordinates are coming? How many variables are coming? 3n, 3 into n. So, 3 into 32, 3 into 42, 126 coordinate Cartesian that equations are coming. So, can we solve it by hand? We cannot solve it by hand. So, let us try to use this one by using variational principle. So, for that purpose what I do, I take a cubic box of 10 angstroms and I will keep this benzene molecule into the cubic box, and in all 3 directions I will take for the discretization I take 50 points in the Cartesian space, 50, 50 and 50 in 3 dimensions. So, if I take like that, okay, so how many operations I need? I need m power 3n. M power 3n operations are required for one iteration. So, m power 3n means I have taken 50 points in all 3 directions. So, 50 power 3n, 50 power 126 operations are required for the matrix diagonalization in real space. Okay. So, if you want to minimize by using the variational principle, you have to find this energy. You have to minimize, if you want to minimize this one, for one iteration you need 50 power 126 operation, but within one iteration you are not going to get the ground state. you need several such iterations, and for each iteration you need 50 power 126 operations. Okay. So, for example, what I assume, I have a fastest computer with me, and that supercomputer, it can perform 10 power 18 operations per second, that is I am assuming. So, my supercomputer is going to perform 10 power 18 operations per second. I am assuming that I have that supercomputer. So, now I want to solve this matrix diagonalization using variation principle, and I have submitted the job there in the supercomputer. So, is it going to, how much time it is going to take? Even the supercomputer with 10 power 18 operations per second, it cannot solve by using variation principle, it cannot give the ground state energy in our whole lifetime. Okay? So, you may get, but how many years? We do not know exactly, maybe my grandchild or my son may see, I may die, I will die after some time. Okay? So, in principle you can solve, but you cannot see that, and all the time you should be backed up, all the time we are having power fluctuation, 5 minutes power gone, we are going to switch off our computer, we have only 5 minutes time. Okay? So, all the time power should be supplied to the supercomputer, and that will perform operations, and that supercomputer is performing 10 power 18 operations per second, but I need for each iteration I need 50 power 126 operations, and several such iterations are required. So, ideally though I can do it with variational principle, though I may get the ground state energy, but I cannot use variational principle for bigger system, because it takes a more than a human lifespan, one human lifespan. So, yeah, so I cannot apply the variational principle, so that is gone. So, now you understood the difficulty of the many body problem. So, we have discussed what is many body problem, 3n dimensional issue is there, and we try to solve it with variational principle. We could not solve by variation principle also, because it is taking years and years. Okay. So, to remove this difficulty of the 3n dimensional problem, people have come up with different approximations, and one such first approximation is Born-Oppenheimer approximation. So, in Born-Oppenheimer approximation, what these people have done, they have assumed the nuclei, they have not assumed, nucleus is heavy, we know, compared to the electrons, because nucleus is having protons, protons are having heavy mass compared to the electrons. So, what they assumed, nucleons are not moving compared to the electrons, because they are slowly moving, but they neglected that kinetic energy, their movement is 0. So, in that case what they have done, nuclei are stationary, so they are not moving, the kinetic energy of the nucleus is 0, and so if you make this one 0, now you can write the fresh Hamiltonian as this one, it is neglected, this is no more involved, it is there, and you can write the fresh Hamiltonian as only kinetic energy of the electrons, electron-electron interaction, and the other two interactions I am merging, and I am saying that that is external potential. So, now the Hamiltonian is transforming into this equation, and now once if I know the Hamiltonian, I can substitute back this one into the Schrodinger equation, and I try to get the solution again. But if you see, though I have neglected two terms, one term I have neglected, kinetic energy I have neglected, but unfortunately the dimensionality problem has not gone. We have neglected one term, but still 3n dimensional problem is there, because if you have n electrons, you have 3n variables. So, though Born-Oppenheimer, they have neglected this kinetic energy of the nuclei, but they could not reduce the dimensionality issues. So, what they have taken, so they have assumed this, they are comparing this nuclei with elephant is heavy and cannot move, but sometimes elephant they run faster than us, that is different issue, but here I am showing that, and electron is like a freebie, so it will move faster. Okay. Yeah, so Born-Oppenheimer approximation also we have dimensionality issue. Now come to Hartree method. So, what is Hartree method? This is called n one particle approximation. Okay, so I have taken the quantum system, now I need to find the ground state wave function for the whole quantum system, maybe zinc oxide or benzene, whatever. So, what this Hartree has done, he has assumed the total wave function. Suppose in our hall we are having some 50 students, 50 electrons are there. Okay. So, the total wave function of this whole system, this hall, is the product of individual wave function of each electron. So, he has assumed the total wave function as product of individual wave function. So, psi 1 into psi 2 into wave function of psi 3 into so on into psi 50. Okay. So, he is assuming the total wave function of product of individual wave functions of the whole system. Okay, that is fine, he has assumed. Now, he is assuming that this is the total wave function. Total wave function means when you substitute this wave function psi into the Schrodinger equation h psi equal to E psi, it should get satisfied because he is assuming that this is the total wave function. So, what he has done, he has substituted this wave function back into the Schrodinger equation and he ended up getting this Hamiltonian kinetic energy plus potential energy part. He got this one, and the last term will tell you the Hartree potential. This is called Hartree potential. Okay. But is it the perfect method? Do we know? Can we claim it? Is it as a perfect method? No. Why? Because the total wave function, he is taking it as product of individual wave function, and if you see this total wave function, it is symmetric in nature. It is symmetric, but electrons are fermionic in nature. So, they should satisfy antisymmetric property and should obey Pauli's exclusion principle. So, this total wave function, it does not obey Pauli's exclusion principle, which is a limitation to this method. So, unfortunately, in Hartree method also we have some shortcoming. The total wave function is not antisymmetric because electrons are fermionic in nature, they should satisfy antisymmetric property, but the total wave function taken by Hartree is coming out to be symmetric. Okay, so, that is one more shortcoming. So, that is what I am writing here. It has not considered the antisymmetric nature of the wave function because electrons are fermionic in nature, and it is not obeying Pauli's exclusion principle. Okay, and the electrostatic interaction, it was treated in average manner because this is average approximation. Okay, and it also will not contain these exchange terms. So, these are the shortcomings that are associated with Hartree approximation. Then we are coming to Hartree-Fock method. So, in Hartree-Fock method, to avoid this symmetric nature of the wave function, Hartree and Fock, they came up with some other approximation. So, they have used this Slater determinant to get the total wave function of the system. Okay, so, this is the Slater determinant. So, in Slater determinant they have written like this, and this gives you the total wave function of the system. So, now the total wave function of the system is given by for n electrons, it is given in terms of Slater determinant. So, for example, if I take 2 electrons, the Slater determinant will be 1 over root 2 factorial pi 1 r 1 into pi 2 r 2, pi 1 r 2 into pi 2 r 1 into pi 1 r 2. So, now this wave function will take care of the antisymmetric nature of the electrons and it obeys the Pauli's exclusion principle. Okay. So, in Hartree method, it is not obeying Pauli's exclusion principle, but here when you consider this Slater determinant, it is obeying the Pauli's exclusion principle because this wave function is now antisymmetric in nature. Okay. So, once if you substitute this Slater determinant total wave function back into the Schrodinger equation and you try to obtain the total Hamiltonian of the system, it will give you all these terms, and this term is Hartree-Fock potential. This one is Hartree-Fock potential, this one. Okay. But there are some problems which are associated with Hartree-Fock method also. Here there is a lack of electron correlation. Electron correlation means, suppose in the system we have 50 electrons, the movement of one electron, how it affects the other electrons, it was not treated properly. Suppose I am one electron, I am moving through the solid, you are all other electrons. So, my motion, how my motion affects the presence of the other electrons in the system was not told clearly by this Hartree-Fock method. So, that is called lack of electron correlation. So, electron correlated movement was not treated in this method. So, this is one shortcoming, and similarly some other shortcomings are also there. It is not suitable for strongly correlated systems, maybe for d orbital and f orbital system it is not applicable, and computationally it is expensive. Some people are doing in chemistry, they use this Hartree-Fock method, and it will take lot of time. Even in WASP also it takes lot of time. So, it is computationally expensive, and overestimation of ionization energies and underestimation of electron affinities, all these are associated with this problem. Okay. So, till now what we have seen? We have seen what is many body problem, what are the problems associated with many body problem. Then we came to Born-Oppenheimer approximation, negligence, but unfortunately these two methods, they are having dimensionality issue, 3-dimensional problem is there. So, we cannot solve Schrodinger equation. Now, coming to Hartree and Hartree-Fock methods also, one method is having a symmetric wave function and another method is not taking this correlation moment of the electrons properly. So, now what I do, I go to density functional theory. So, what is density functional theory? What is the need for the density functional theory? So, when I was discussing about this many body problem, I have 3n variables. Okay. So, suppose for example, if I transform these 3n variables into 3 variables, my life is easy, right. So, so if I transform these 3n variables back into 3 variables, I can solve it because we have done it for hydrogen atom also. So, what I do, these 3n variables, I just want to transform into 3 variables and I need some parameter which I can express in terms of 3 variables. Okay. So, that is what I am exactly looking for and it is given by electron density of the whole system. So, the electron density can be expressed only in terms of spatial coordinates nx, ny and nz. So, for this purpose what Thomas and Fermi they have given in 1920, they have expressed kinetic energy in terms of electron density. I did not write here kinetic energy they have expressed in terms of electron density. So, this whole DFT is dependent on two theorems, Hohenberg-Kohn theorems, and Hohenberg-Kohn theorem first one will tell you the ground state energy of is a unique functional of the electron density. So, you can express ground state energy in terms of the electron density. And the second Hohenberg-Kohn theorem, it states that the electron density that minimizes the energy, because we need ground state energy, minimum ground state energy. The electron density that minimizes the energy is the true electron density. Okay. So, you are feeding the electron density to get the minimum of the energy and you get the minimum energy and corresponding that electron density. Okay. Electron density that minimizes the energy is the true density. So, by playing with the electron density, I will get the ground state energy. Okay. And I know ground state energy is unique function of the electron density. So, my aim is to find out the electron density that gives the minimum energy. If it gives the minimum energy, the corresponding electron density is the true electron density. Okay. So, there is a proof for these two theorems which are not required here. So, based on these two theorems, density functional theory is built. So, by using these two theorems, Kohn and Sham, what they have done, they have modified this Schrodinger equation into Kohn-Sham equation. This is known as Kohn-Sham equation. Here the kinetic part is there, external part is there, right. Hartree, this part is there and this exchange correlational part is there, which is equal to this energy. Okay. So, here you can find out the energy, this ground state energy into this all these terms. Here everything we know, this is the external energy, this is the Hartree energy, this is the kinetic energy, the only term that we do not know is the exchange energy. Okay. So, all things we are doing in DFT is to find out the ground state energy. In ground state energy all things can be known except this one, exchange correlation energy. So, what is exchange correlation energy? Exchange correlation energy I told you already. Correlation energy is correlated movement of one electron, the presence of one electron movement. Okay. How it affects the other electrons, nobody knows. And similarly, what is exchange energy? If you exchange 2 electrons in the system, how much energy it costs? But we have many electrons in the system, we are not talking about 2. That also it is computationally expensive, nobody knows. So, all terms we know except this exchange correlation energy, and this exchange correlation energy people have given some exchange correlational functions which are known as LDA, GGA, HSE, and in Gaussian you say B3 leap, some sets are there, right, basis sets, yeah, exactly. So, the self consistency loop for DFT I am giving like this. So, first I will give some input ground state energy that will be taken by the crystal structure itself, it will generate some energy, that electron density. So what I do, I have to solve the Schrodinger equation. Schrodinger equation is H psi equal to E psi, H equal to kinetic energy plus potential energy. This energy in the form of electron density. Now what I do, I will give some guess density, because this is generated already, and also I will set some energy convergence criteria. Cutoff energy I will give some 10 power minus 6 electron volts, or here it is giving how many? 1, 2, 3, 4, 5, 6, yeah, 10 power minus 6 electron volts. So this density, initial density is supplied, electron density. This initial electron density we are going to keep here. So you will solve it, you will get psi and epsilon, but whatever the density, fresh electron density, if it is less than the old density, then it will go here and it will give the fresh electron density again. So these iterations will continue, but the moment when the updated density is equal to the old density, this will be stopped and it will give you the ground state energy. Okay, so we will get ground state energy in terms of the electron density. So this is called as self consistency loop, SCF calculation. So these are the basics about the DFT. So in DFT we have the self consistent field calculation, and as I told you already, we don't know exchange correlation energy exactly, right. So in Kohn-Sham equation we are getting total energy in terms of the electron density E rho. In E rho every term we know except EXE, exchange correlation energy, and these exchange correlation energy functionals are given by different approximations. One first approximation is LDA, local density approximation. So in local density approximation they have assumed that the density is varying linearly, very slowly with time. Okay, and for that they have given some expression, and you can use that expression and you can do the calculation, and that is called as LDA. So we are doing DFT in LDA approximation. Similarly, but some of the problems are associated with the LDA. When you optimize the system, it give you the lattice constants which are less compared to the experimental lattice constant. So to avoid that, people have come up with generalized gradient approximation. So they have taken the gradients of the electron density also. In that case, some of the improvements can be made. Here you are getting the lattice constant may be overestimated compared to the experimental ones. So here also it is having some kind of difficulty, but together LDA and GGA, exchange correlational functionals, will give you wrong band gaps. It will not give you exact band gaps. If you want to get exact band gaps, you have to use some other functionals which are called as hybrid functionals, HSE, MBJ, GW approximation, and meta GGA calculations you have to do. But all these hybrid functionals, they will cost you more. They are computationally expensive. If I use LDA and GGA, I may finish my calculation in 2-3 days. But if I use HSE and this meta GGA scan functional, it may take 3 months. So once if you submit job on the computer, you have to wait for 3 months. You may get some wrong exact result, but computationally it is expensive. We have to wait. Yeah. Oh. How to make it full screen? No. Full screen is exited. Yeah, for his contributions to the density functional theory, Walter Kohn, he was awarded Nobel Prize in 1998 for the development of density functional theory. Okay, so he has developed this theory proof in 1964 and he got the Nobel Prize in 1998 in chemistry. So based on this density functional theory, I will try to discuss some of the results that I have obtained for my compound using density functional theory. So what I have done, I have calculated thermoelectric properties of the gentle phase compound Ca2Zn2. So since I am talking about the thermoelectricity, so we need to know some energy problems. So I will focus on energy materials, and we know that nowadays there is a great demand for the energy. Everywhere energy is needed. 10 years back, if you go villages, people were not using any AC, fridge, TVs, of course they were using. Okay. But nowadays if you go to village, every home is having, of course one should have, every home is having AC, fridge, refrigerator, microwave, all those things are there. But they need electricity, energy. How to get that? If you go to Andhra Pradesh sometime back in 20 years back, we used to get only 2 hours current, 3 hours current, that to night time. Whole day we were waiting for current, no electricity. Okay. So there is a great demand for the energy, and all the time we are using mobiles, and these mobiles, many students what they do, whether they are talking or it is in charging mode. It is not means like they don't leave it as such. They are either talking or in charging mode. For that also you need energy, right? So I'm sorry. So what are the current problems associated with the energy? We know increasing pollution. This increasing pollution will give you a lot of problems, greenhouse emission, all those things, right? We need to look for some other energy sources. Whatever the natural sources we have, gas, oil and coal, these are depleting day by day, and maybe after 50 and 100 years, this coal is not existing anymore. We are digging, nothing will come after some time, because you have to allow some time, 2000, 3000, then only that will develop. Okay, we are digging more than what is required. So coal is gone after 100 years, no oil, no gas, nothing is there in the core of the earth. So we need to look for some alternative solution, and that alternative energies that come with some alternative energy sources, and one such energy source is solar energy, wind energy, tidal energy. So there are many energy sources, and one among them is thermoelectric energy. So in thermoelectric energy, we can generate the electricity from the waste heat recovery. From waste heat, we can generate the electricity based on the Seebeck effect. So I focus on this alternative energy, and of course this workshop is also environmental nanotechnology. I am not doing nanotechnology, but I am doing some environmental friendly energy resource calculations. So that is thermoelectric energy. So which gives you the electricity from the waste heat. So what is thermoelectricity? The materials which convert heat into electricity, they are known as thermoelectric materials, and they are based on Seebeck effect. In Seebeck effect, we have two junctions, hot and cold junctions, and due to the temperature gradient between these two hot and cold junctions, that will give you some voltage which is known as Seebeck voltage, and this effect is known as Seebeck effect. And we can find out the Seebeck coefficient S equal to minus delta V by delta T. Okay, so based on this, we can try to harvest some energy by using this alternative thermoelectric effect. So we have some applications on this thermoelectric materials. For example, if I take some people have means like some companies have already developed few applications, and one such one is Citizen Eco Drive Thermo Watch. So how it operates? It converts the temperature difference, because watch we are wearing. Okay, so it is touched to hand. So it converts the temperature difference between body and the surrounding air. There is a difference, delta T. So temperature difference between body and the surrounding air into electrical energy, and that is enough to run the watch. You don't need any particular battery, and here no battery is needed, and its operation time from full charge. After full charging, operation time is 6 months. That means approximately 16 months in power saving mode. Power saving mode में रखेंगे तो 16 months होगा, हम नहीं रखेंगे 6 months तक चलेंगे, ठीक है? Okay, so this is one application of the thermoelectricity. On the second application, in automobile applications, we have this one. Or we are driving car. In car, there is a lot of waste heat is generated. Suppose if you can use that waste heat to develop some thermoelectric device, a thermoelectric generator, that is beneficial, and that will give you that will save you some petrol, right? So here, what this BMW company has done, it has manufactured this thermoelectric generator by using the waste heat generated inside the car. So what they are doing, waste heat generated in the car is converted to electrical energy, and this energy can be used into internal parts which increase the fuel efficiency. So this kind of thermoelectric generator you can see in BMW series 5 make model 2010. So it is attached with gasoline engine with thermoelectric generator. So in car we are getting waste heat, and that is converted into, and we can have some other application also in defense applications. If you see soldiers, sometimes in news we watch, soldiers are carrying lot of weight. पीछे बहुत weight है, lot of weight they are carrying, and they are having some AK-47 gun, they are running. Sometimes they have to climb mountains also. So is it possible to carry some 20-30 kgs all the time? No. And they are carrying some electronic gadgets, and electronic gadgets they are having batteries, right? So what we try to do, we try to reduce the weight of the soldier by using this thermoelectric technology. So whatever the electronic gadgets or instruments they are carrying, if we are replacing them with thermoelectric technology, then we can reduce the weight of the soldier by almost 30%. So that way this thermoelectric technology can be used. So what it will do, it converts the temperature difference between the soldier's body and the surrounding into electric energy, and that may be used into some device which may be useful for the military applications. So this is also one such applications using thermoelectric materials. Yeah. So we need to find the thermoelectric materials with high figure of merit. So what is figure of merit? Figure of merit is a dimensionless quantity which quantifies the whether this material is suitable for thermoelectricity or not. If you are getting high figure of merit ZT, then it is most suitable for the conversion efficiency is more from heat to electricity. So it is given by the formula ZT equal to S square sigma by total thermal conductivity Ke plus Kl, where Ke is the electronic part of the thermal conductivity, Kl is the lattice part of the thermal conductivity. S square sigma is known as the power factor, where capital S is given by the Seebeck coefficient, we have seen that already. Sigma is the electrical conductivity and T is the absolute temperature between hot and cold junctions. Okay. So by looking at this formula, we have in numerator S and sigma, and in the denominator we have Ke and Kl. So if denominator is less, Gt is more. If numerator is more, Gt is more. So our aim is to increase power factor S square sigma so that Gt is more, or otherwise our aim is to decrease the total thermal conductivity Ke plus Kl. Okay. So the good thermoelectric materials, they should possess high S so that Gt is high, high sigma so that the figure of merit is high, and low lattice part of the thermal conductivity. So we need to look for such materials where S is high, sigma is high, and lattice part of the thermal conductivity is less. So how to choose the materials? So what kind of materials I have to choose? So we have materials, metals, semiconductors and insulators. So if I am talking about metals, electrical conductivity is very high. We know copper wire is copper, aluminum, silver, all those wires are highly conducting, conductivity is very high. That's good. But unfortunately, if you come to Seebeck coefficient, because we need also high Seebeck coefficient for high figure of merit, it is very low. And thermal conductivity is also very high for metals. So metals are not suitable for thermoelectric applications, because if you see the figure of merit formula, S and sigma must be high, but sigma is high, S is very low, and K is also very high. K should be low, our expectation is low. So metals are not suitable for thermoelectric applications. When you come to insulators, conductivity, electrical conductivity is extremely low. They are insulators, so they are also not applicable. Seebeck coefficient is high, again this one is low, but this one is very low. So this is also not applicable. So now you come to semiconductors. Semiconductors, electrical conductivity is maybe moderate, but here you have high Seebeck coefficient and low thermal conductivity. These two parameters, they are deciding whether to choose semiconductors are suitable for thermoelectric applications or not. So we can say that semiconductors are a good platform to study the thermoelectric characteristics. Okay. So now we have decided among metals, semiconductors and insulators, semiconductors are the best material for which we can explore thermoelectric properties. So what I have done for my compound, I have used Vienna ab initio simulation package VASP for my electronic structure calculations. Then I have studied the vibrational properties by using PhonoP and Phono3Pi codes, and thermoelectric properties they are explored by using AMSET code, and this AMSET code uses semi-classical Boltzmann transport theory. And thermal conductivity has been calculated using empirical Slacks model, and I have also used Phono3Pi code to obtain the thermal conductivity. So as I told you already, I have taken this gentle phase nitride Ca2ZnN2, and this is a periodic solid. It exists in the crystal structure, tetragonal crystal structure with space group 139, and the conventional cell is shown here. In the conventional cell, how many number of atoms we have? We have 2 calcium atoms, 2 zinc atoms and 4 nitrogen atoms. So what I have done, I have optimized this conventional cell by using exchange correlation energy functionals PBE and PBE sol, both are GGA functionals, and after optimization I have seen that the volume of this PBE is coming close to the experimental one. So, I have continued all my calculations with PBE exchange correlation functional. So, once if I get the optimized conventional cell, I have converted into primitive cell, and this primitive cell is having 2 calcium. This is the primitive cell of the conventional cell. This primitive cell is having 2 calcium atoms, 1 zinc atom and 2 nitrogen atoms respectively. And I have calculated all these calculations in reciprocal space in the first Brillouin zone, and the Brillouin zone high symmetry points are also shown here. So, immediately after the optimization I have to check for the stability. There are different types of stabilities are there: chemical stability, thermal stability, mechanical stability, dynamical stability. So, I have checked few stabilities. The compound is whether mechanically stable or not, it can be ensured by a Born stability criteria, and for tetragonal structure the Born stability criteria is given by these expressions, and from the obtained elastic constants all these criteria are getting satisfied, implying that the compound is mechanically stable. And I can find out the Young's modulus E and bulk modulus B, I have calculated, and if you are having high Young's modulus and high bulk modulus, indicates that the compound is highly rigid and hard. And the obtained the calculated B by G ratio is 1.75, and sigma is greater, the Poisson ratio is sigma is greater than 0.26. If these two conditions are getting satisfied, the compound is ductile in nature, otherwise it is brittle. So, here the studied compound is ductile since these conditions are satisfied. And Debye temperature is the characteristic temperature of a solid, which differentiates the high and low temperature regions of a solid, and we are getting the high Debye temperature for the studied compound 418 Kelvin. So, the compound is mechanically stable. Then I try to study the dynamical stability by using the molecular dynamic simulation. What I have done, I have taken up to some time, I try to calculate the root mean square displacement, and this root mean square displacement, it is almost stable over the studied time from 0 to 16 picoseconds, implying that the compound is at 500 Kelvin. So, at 500 Kelvin up to some time the compound is thermally stable, implying the thermal stability in this compound. Then I calculated phonon dispersion of the compound. The positive phonon frequencies will give you the dynamical stability in this compound, and the phonon DOS, from phonon DOS we can tell that in which region what type of atoms are contributing. And we know that the atoms with heavy mass, they will vibrate with low frequency, the atoms with light mass, they will oscillate with more frequency. And if you see here, we have only 3 atoms, calcium and zinc, and nitrogen. So, nitrogen is light mass, so it oscillates with high frequency if you see nitrogen, right. Similarly, zinc is compared to these ones, zinc is heavy atom, so zinc is oscillating here since it is having heavy mass. So, what atoms contribute in the what region to the what kind of vibrational modes will be known by this phonon dispersion. Then I have calculated the electronic structure of this atom. By electronic structure calculations, you can find the nature of the band gap, nature of the chemical bonding, what kind of effective mass you can expect, all those things you can study through electronic structure. So, electronic structure I have calculated by using PBE functional without spin orbit coupling and with spin orbit coupling along the high symmetry path, and you can see that the band gap is coming around here. So, it is not a direct band gap because momentum vector is not converging here. So, indirect band gap semiconductor having this much band gap, and this band gap without spin orbit coupling is coming out to be 0.74 electron volts, with spin orbit coupling it is coming out to be 0.73 electron volts, but both these band gaps they are not matching with the experimental band gap. What is the experimental band gap? 1.62 electron volts, but if I want to get the correct thermoelectric properties, I have to match the calculated band gap exactly with the or nearly with the experimental band gap. So, PBE and PBE without spin orbit and with spin orbit, they are not giving some fruitful band gaps. So, what I have done, I have used some hybrid functional, MBJ functional I have used using WASP. This time I have calculated the band gap by doing the density of states calculation. If you see here, the total density of states, you can see that this is band gap here, this is valence band and conduction band, and here it is band gap, you can see this. So, this band gap is coming out to be 1.67 electron volt, which is closely somewhat matching with the 1.62 electron volts experimental band gap. And you can see that from this graph which orbitals of the which atom are contributing in which region. calcium p orbitals are contributing, which region you can study by using the partial density of states, you can see from the figure. So, later on what I have done better charge analysis for the studied compound. So, I have calculated how much charge is flowing from which atom to which atom during the process of this crystal formation, and I concluded that I know the Pauling electronegativity values, we know from the periodic table. Pauling electronegativity values, calcium, zinc and nitrogen atoms are given by these values, and Pauling electronegativity is high for nitrogen, 3. Pauling electronegativity value is 3 for the nitrogen atom, and we know very well know that the elements with higher electronegativity, they will attract the charge from the lower electronegativity elements. Elements with higher electronegativity, they will attract the charge from the lower ones. So, therefore, from that logic, nitrogen should attract charge from calcium and zinc. And how to confirm that? So, better charge is giving that, and we can check the same from the charge density plot. So, what I have done, I have plotted charge density along 1 0 0 plane. In this plane all atoms are covered. So, we can see that the elements calcium and zinc are having low electronegativity values. So, nitrogen attracts charge from calcium and zinc atoms, that can be seen from here, and the amount of charge how much is transferred I have written here. The better charge on calcium, zinc and nitrogen are 1.41 electrons, 0.48 electrons respectively, and these are losing charge and are accepted by nitrogen atom because it is having 1.6 electrons. Okay. So, nitrogen is having higher electronegativity value which attracts the charge from the lower ones calcium and zinc. So, this is the better charge of this one. So, in order to predict the accurate thermoelectric properties, we need to estimate the carrier lifetime. If you want to estimate the carrier lifetime, you have to go, you have to find the scattering rates of the lifetime carriers, maybe p-type carriers or n-type carriers we have to find. So, the scattering rates are approximated by using Fermi's golden rule, where it is given by this formula, where this G and M is given by electron phonon coupling element, and this electron phonon coupling element is different for different scattering mechanisms. There are 3 scattering different mechanisms that I have studied. One such scattering mechanism is acoustic deformation potential scattering, ADP, ionized impurity scattering, IMP, polar optical phonon scattering, POP, ADP, IMP, POP. And this ADP is due to the interaction of the electrons with acoustic phonons, and ADP dominates at low energies and low temperatures. Its scattering rate is proportional to T into energy. It is basically elastic in nature. Similarly, when it comes to ionized impurity scattering, it is due to the Coulomb interaction between the charge carriers, maybe p-type or n-type, and charged particles, and it is significant at low temperatures and high doping, and scattering rate decreases with higher carrier energy, and it is also elastic in nature. Both are elastic in nature. And when it comes to polar optical phonon scattering, POP scattering, it is caused by interaction with the longitudinal optical phonons in polar material, and it is important in polar semiconductors and at high temperatures, and it strongly affects the mobility and the electrical conductivity. It is inelastic in nature. So, these 3 scattering mechanisms I have studied, and I found the scattering rates and hence carrier lifetimes. So, for all these 3 scattering types, I have given this electron phonon coupling matrices, and for my compound I have studied these 2 are for n-type. N-type means electron concentration is n-type, and this is for p-type carriers at 10 power 19, 10 power 20, 10 power 19 and 10 power 20. So, up to 500, 100 to 500 temperature by varying that I have studied, and for all the cases the scattering is increasing with temperature, and you can see that the scattering rate is mainly due to the POP scattering, POP. So, why is it so? Because the POP scattering is governed by the difference between the static dielectric constant and high frequency dielectric constant. I have calculated static and high frequency dielectric constants, and the difference is coming more. If the difference is more, then we can say that it is due to the polar optical phonons. So, from this logic, we can say that the POP scattering among the 3 studied scatterings, POP is more dominant compared to other 2 scattering for both n-type carriers and p-type carriers. So, once if you know the scattering rate, inverse of the scattering rate will give you lifetime. So, we can find the carrier lifetime for 2 concentrations for both n-type and p-types. So, we can see that as a function of temperature, the carrier lifetime is decreasing monotonically. Why it is decreasing? If you increase the temperature, there is more phonon activity. Due to that one, scattering rate is more. If the scattering rate is more, lifetime is less. And you can see that for both type of carriers, it is decreasing. So now I know carrier lifetime, and this carrier lifetime is used to calculate the thermoelectric property. Then I have estimated lattice thermal conductivity by using the Slack's model, which is purely empirical model. So in Slack's model, it depends on this Grunesian parameter which gives you the enharmonicity in the crystal, and this is absolute temperature, and theta d is the I found that Debye temperature. So I know Debye temperature, and all these parameters I know, and I can find the lattice thermal conductivity as a function of temperature. And also I have used phono 3 pi, which relatively gives more accurate thermal conductivity. So I can get the thermal conductivity tensor here. So by using these two methods, I have calculated the lattice thermal conductivity as a function of temperature, and for both models, the trend is same, but it is decreasing. So it is quickly decreasing up to 200, then it is decreasing slowly, and the higher value of gamma means Grunesian parameters, which tells you the enharmonicity, and low theta d, it will give you the, it may give you the low KL values, but since we have here theta d is more, so we may expect higher thermal conductivity values, which are not good for high figure of merit. But unfortunately for this compound, we are getting high theta d value and higher enharmonicity gamma value, so it may give you some high thermal conductivity, which is not desirable, because generally ultra low thermal conductivity is expected, maybe sometimes it may be less than 2, but here it is starting at 45, which is not desirable. So what we have done, we tried to calculate the mobility also for p type and n type for different concentration dopings. So we can see that the mobility is higher for hole type doping, indicating that p type nature of the compound. It is p type, because for p type the mobility is more, so indicating that it is p type in nature. Then we have calculated electrical conductivity also as a function of carrier concentration, and also as a function of temperature for different dopings, as a function of carrier concentration for different temperatures, and up to 10 power 19 there is no significant increase in the electrical conductivity, and after that it is increasing, and you can see that the electrical conductivity for p type doping is more compared to the n type doping. The dashed ones are p type dopings, and it is consistent with mobility values, because for mobility also p type is more, mobility values are also more for p type, and therefore the conductivity is also more for p type here. And also we can see that the electrical conductivity for both cases, for both doping, it is decreasing with temperature, okay, because if you increase the temperature, it increases the lattice vibrations. At the higher temperature, due to the increased lattice vibrations, it will enhance the phonon scattering, so that gives rise to the decrease in the electrical conductivity of the material. Similarly, what I have done, I have calculated the electronic part of the thermal conductivity. For semiconductors, lattice part of the thermal conductivity plays a important role, but we can find out electrical conductivity also. So with carrier concentration, up to here there is no negligible increment, but after 10 power 19 to 21 there is a significant increase in the thermal conductivity with the concentration. And also if you increase the temperature, the thermal conductivity lattice part electronic part of the thermal conductivity decreases, okay. So why it is decreasing? Due to the increasing electron phonon interactions. And another important parameter is Seebeck coefficient, which is placed in the numerator part of the figure of merit. So we can see that with carrier concentration, the Seebeck coefficient is decreasing. It is decreasing with carrier concentration, but with temperature the Seebeck coefficient is increasing. And you can see that for n type Seebeck coefficient is more. For n type Seebeck coefficient is more, but for p type conductivity is more. So finally, so here for n type Seebeck coefficient is more, and here we have given the reason. It increases with temperature. For both n type, S is more, okay. And what is the reason for higher S value? It may be due to the higher density of states, due to the effective mass. Effective mass is coming from the band structure characteristics. Okay. So, if you have a parabolic thing, if you have a flat band, you have heavy effective mass, heavy holes or heavy electrons. If you have parabolic, you have lower effective mass. Then coming to power factor. So, power factor is also an important parameter which tells you the how much amount can be converted from heat to electricity, So, we have found the power factor as a function of carrier concentration for different temperatures and as a function of temperature for different dopings. And you can see that the carrier concentration is from 10 power 18 I have taken, it is increasing up to some extent here, and after that for 1 point it is decreasing. And similarly, here also you can see that initially it is decreasing with increasing temperature, okay, due to the phonon scattering at enhanced temperature, elevated temperatures. But though the n-type carriers, they are exhibiting high Seebeck coefficient. If you go back, n-type carriers are having high Seebeck coefficient, but power factor is slightly higher for p-type carriers. Power factor is slightly higher for p-type carriers, as can be seen from the graph. So, once if I know the power factor S square sigma I know, Ke plus Kl I know, for different concentrations I know, for different temperatures also I know. So, once if I know the power factor for different concentrations and different temperatures, and I can plot figure of merit as a function of carrier concentration and as a function of the temperature. Okay. So, here you can see that the figure of merit is increasing with carrier concentration for different temperatures, and at the same time this one also, it is also increasing with as a function of temperature, figure of merit is increasing for different dopings. I have studied only for 10 power 19 and 20 dopings because they are significant for semiconductor range, 19 and 20 are important. So, for 19 and 20 you can see that here for p-type the figure of merit is coming out to be more p-type. So, you can say that the material under study is basically p-type dominant, because GT is more, and we have seen that also. For power factor is also coming out to be more for p-type carriers compared to the n-type carriers. So, we can see the figure of merit is higher for p-type for 10 power 19, 10 power 20 it is even more also, we can see that. And what we have done, we have compared our obtained results with the literature, existing literature, and we are getting some comparable values and some are low, and these are from the literature, similar literature, and this is the compound that I have studied, and they are somewhat low. And the low figure of merit values, it is attributed to the higher band gap. The material that we have chosen is having band gap 1.62, but for thermoelectric materials we have to take narrow band gap semiconductors, but we have chosen this one. So, that is why we are getting small band gap, small figure of merit values we are getting. So, finally, I can say that in conclusion, I can say the gentle phase tetragonal compound, it is found to be stable mechanically and dynamically and thermally. Obtained band gap values PBE using PBE and MBJ functionals are 0.74 electron volts, 1.6 electron volts respectively. Band gap using MBJ functional, it is exactly matching with the experimental one, and lattice thermal conductivity, it is estimated using empirical Slacks model, and phono 3 pi also we got. From phono 3 pi we got somewhat lower KL value compared to the Slacks model, and we have explored different types of scattering mechanisms, 3 types, ADP, IMP and POP scattering mechanisms, and among the studied scattering mechanisms, POP scattering is dominating due to the difference between the static and high frequency dielectric constants, and the average mobility also we have studied as a function of temperature, and for n-type carriers it is more because of the lower effective mass of the electrons, and the thermopower S, Seebeck coefficient is also known as thermopower, it is more for n-type, but unfortunately power factor is coming to be higher for the case of p-type carriers because of the higher value of the Seebeck coefficient. And finally, if you come to figure of merit, GT is found more for p-type carriers. So, for higher GT you need to get GT up to 2, but we are getting 0.07 something like that only, but if you screen more materials in future with less band gap you may get 1 or 2 something like that. But as of now we are getting only 0.07 figure of merit, which may be tuned to get higher GT values, and these study results are accepted for publication in Physica Status RDB recently last week. I acknowledge DST Serb for funding this research through grants, EQ and CRG, and I also acknowledge Kepler facility at IISER Calcutta. I thank my collaborator Bemalang Chatari for giving me computational facility at IISER Calcutta. And this is my research group. Thank you.
Thank you, sir, for a nice lecture. Now session is open for discussion. Any queries?
So how to generate MGV hybrid pseudopotential?
Actually, there are different kinds of researches. Okay, one part of research is generation of pseudo potentials, and we are not doing that. We use the pseudo potentials given by WASP, because once if you generate pseudo potentials, you have to test that pseudo potentials for different systems. Suppose you have generated a pseudo potential for calcium. For my material, that pseudo potential may work, but for calcium oxide it may not work, because calcium is having a number of structures, right? So you have to test. That is separate research. So we don't generate pseudo potentials. We use pseudo potentials already generated by WASP community. So are you generating or what? Huh? Huh? अच्छा, तो आपने किया ना कभी? Generate I don't do, but mix I do. Yeah. How to do that? Suppose if I am using MBJ functional using WASP. Okay, so there is some parameter alpha and beta, and alpha and beta you have to change. You have to tune to get the desired band gap. So what I do, I submit, I take 0.1, 0.5, 0.7, 1.1. Okay, whatever the band gap is matching, and I will take that one. But not, that is not generation.
Any other question? If there is no any query, then let's congratulate Dr. Nanotechnology. He has explained all the things from. Thank you, sir, for your talk. So I actually use the DFT for energy optimizing of superimposed structures. So in my case, we actually synthesize many large structures comprising of many atoms and molecules. For that case, sometimes we could not converge the energy by using DFT. So for that functional basis set, we need to
Changes.
So how to choose the functional basis sets and how to get many occasions we could not get a energy minimized structure. So what does not converge?
Actually, there is no particular method. Suppose if you are working on some particular set of compounds, suppose I am working on some magnetic systems. Okay, so magnetic systems, they don't converge. So we have some parameters, A max mix, B mix, B max mix, some parameters are there. You have to change those values. Luckily, if you convert, that's fine. So that is why what people do for magnetic system, they don't go for 10 power minus 6 electron volts convergence. They do only for 10 power minus 4. And they report the same also. So that comes through experience. That is the headache that we have.